It seems like time is the only thing we can always count on. It never stops, never moves forward, and never ticks off. But what if there is no such thing as time? We might not be floating on a cosmic river. It might just be a trick of the mind, or a result of physical rules we don't fully understand. From the bent edges of black holes to the frozen light of faraway galaxies, the universe is full of signs that time might not be basic, or that it might not even exist. You can't hide the cracks once you see them. It's time to face the uncomfortable truth. Time may be the biggest lie of all. The fabric of space-time, and why time might not be a thread. Picture space without time, like a movie that doesn't have any frames. You'd have a room, a planet, or even a galaxy that is frozen solid. Think about time without space, just time. But where are the ticks? There's nothing to check. That's what science had a problem with before Einstein changed everything. Before the 20th century, scientists treated space and time like separate ingredients. Space was the stage. Time was the clock. Newton saw time as absolute, something that marched forward, the same for everyone, everywhere. But Einstein said, nah, that's not how it works. In 1905, with special relativity and later with general relativity, he introduced a mind-bending idea. Space and time are one thing. A four-dimensional fabric we now call space-time. You're not just moving through space when you walk down the street. You're also moving through time. Every single object with mass, energy, or even just velocity shapes this fabric. And in return, the shape of the fabric tells everything how to move. That's gravity. Not some invisible force like Newton thought, but the result of mass-bending space-time. Planets don't orbit the sun because the sun pulls them. They follow curved paths carved into the fabric. In this fabric, time doesn't flow like water. It's more like a direction. Just as you can go left or right in space, you're also going forward in time. But in that direction, it's not always stable. There are now scientists who say that time is not a real dimension like space. We do describe it as a fourth line in our equations, but it acts in a different way. Time can't be moved back and forth, but space can. Time moves in only one direction, and sometimes time just goes away when you study quantum physics or string theory. For example, in certain equations of quantum gravity, you can describe the universe without any reference to time at all. Everything is just a collection of relationships between events. No ticking, no now, just a vast frozen tapestry. It's called the timeless universe idea. And yeah, it's weird. In fact, Julian Barber, a physicist, says that what we call time is just a way to arrange different moments in the world. It's like looking through a picture book. Every page is there. There is no real movement between them. Your brain only thinks you're going through change because it connects those snapshots in a way that makes sense. Einstein himself hinted at this. When a friend died, he wrote in a letter, "For us physicists, the distinction between past, present, and future is only a stubbornly persistent illusion." Translation: time might just be a trick of perception. Even more unsettling, in space-time, all moments exist. Not just the one you're in. Your birth, your death, every awkward Zoom call you ever had, they're all there, frozen into the cosmic fabric. You're just riding the wave, experiencing them one slice at a time. That idea, by the way, leads straight into the block universe theory, but we'll get there later. So, what's making it seem like time is moving if it's just a part of a four-dimensional world that doesn't really flow, but just is? Some people say it's entropy. Some say it's their memory. But there's no way that it's a clock. The relativity of time. No two clocks tick alike. Time seems to be personal. You look at your watch, the wall clock, and the microwave countdown. Everything seems solid, steady, and light. But when you leave your normal environment, things break. Because the truth is that time is not the same for everyone. It bends. It gets longer. It's not honest. Your clock will tick differently than someone else's if you're moving quickly or sitting close to something really big. This isn't just an idea. This is a cold, hard fact that has been proven. Einstein's theory of relativity is where this whole mess of ideas ends. Special relativity and general relativity are the two kinds. First, let's talk about special relativity. It says that time changes based on how things move. It takes longer to move through time than it does through space. And no, that is not science fiction, if it sounds like that. Atomic clocks that were taken on jets, shot into space, and left running in labs have all been used to test it. They are a little out of step when they get back. not because the clocks are broken, but because they've actually had less time. Let's say you have a spaceship that is traveling very fast, almost as fast as light. There is a clock on board. There is the same clock back on Earth. The person on the ship thinks that everything is fine because they eat, sleep, and live. The two clocks don't match when they get back to Earth, though. The one on Earth kept going at a normal speed. The one on the boat, it was behind. The time it spent was shorter. Time really does slow down like that. But speed isn't the only thing that messes with time. Gravity does too. That's where general relativity comes in. According to Einstein's math, massive objects like planets, stars, and black holes warp space-time, and the stronger the gravity, the slower time flows near it. This means a clock at sea level, closer to Earth's mass, ticks slower than a clock at the top of a mountain. Not by much. We're talking nanosecond, but it's measurable. This effect, called gravitational time dilation, also shows up in extreme environments. Near a neutron star, where gravity is crushingly intense, time slows dramatically. Hang out near a black hole, time practically stops. More on that later. But even in our day-to-day world, this effect matters. In fact, without accounting for relativity, your GPS wouldn't work. GPS satellites orbit above Earth, where gravity is weaker and speed is higher. Both of those conditions make their onboard clocks tick slightly faster than clocks on Earth. If engineers didn't correct for that difference, GPS would be off by kilometers. Every day. Einstein's weird equations keep your Uber from dropping you off 2 blocks away. Let's make this more like a conversation. Let's say 2 people share a birthday. One lives their whole life on Earth. The other person becomes an astronaut and flies at almost the speed of light for years. Their ages will be different when they meet again. The twin who is stuck on Earth has more wrinkles. The astronaut is younger. He or she doesn't just look younger. That is not just a story from the movie Interstellar. That's just basic science. We like to think of time as a shared experience, but in the universe, there's no now that applies to everyone. Every observer has their own version of time, their own now. If you're moving fast or hanging out near a massive object, your now isn't the same as mine. The idea that time is what a clock measures sounds clean until you realize every clock tells a different story depending on where it is and how it moves. There is no master clock, no universal beat, just a chorus of ticking, each slightly off, creating a reality that feels stable but isn't. It's hard to keep track of the past, the present, and the future. In some frames of reference, 2 things that happen at the same time to one person may happen at different times to another. Like, 2 blasts on Earth might look like they happen at the same time. As a person flew by in a spaceship, though, one happened before the other. Time changes places. The truth itself gets cloudy. That's why some physicists say time isn't fundamental. It's emergent, like temperature, which comes from molecules moving around. Time might not be a thing on its own, but something that appears when certain conditions are met, like motion, mass, or perception. So when you glance at your clock, don't be fooled by its neat little ticks. It's not the ruler of the universe. It's more like a local dialect in a galaxy of strange accents. In space, with enough speed or gravity, even those ticks lose their rhythm. Some fast, some slow, some not at all. Time dilation around black holes, when seconds turn to centuries. Do not worry, you are not falling into the black hole. You are just floating near the event horizon. The parts of your ship are stable. Your heart is beating fast. Your friends on Earth, on the other hand, are watching your fall live, and something is not right. You are moving less quickly. You give a wave. It takes a while for your hand to come up. Your look stops in the middle of it. For them, it seems like time has stopped. But for you, everything seems fine. In the area around a black hole, time slows down. It changes everything we know about time. We already know gravity bends space-time. The stronger the gravity, the more extreme the bend. A black hole is the ultimate gravity well. Its mass is so concentrated that not even light can escape its pull. That boundary is called the event horizon, a point of no return. But the real mind trip is what happens to time around it. As you get closer to the event horizon, space-time becomes increasingly warped. From a distance, someone watching you sees your clock tick slower and slower. The closer you get, the more stretched time becomes. At the very edge of the black hole, your seconds might look like hours, or even centuries, to an outside observer. You could spend 10 minutes chilling near the event horizon, but millions of years could pass outside. This isn't some sci-fi stretch, it's real physics. The equations of general relativity predict it, and it's been tested on smaller scales. Time dilation has been observed using super-precise clocks placed at different altitudes on Earth. It's just way more intense near a black hole. So what does that mean for time itself? It means time is elastic, flexible, not universal, not fixed. It bends in the presence of gravity, and nowhere is gravity stronger than a black hole. The person falling in never feels anything change. From their point of view, time keeps moving forward as usual. Their heartbeat stays steady, their brain processes normally. But to everyone else, it's like they're slowing to a stop. This split in perception is one of the wildest implications of general relativity. It's not just a mind trick, it's a physical reality. Want to go even further? Think about this. If you could use some crazy sci-fi rocket technology to stay just outside the event horizon forever, you'd be moving much more slowly than everyone else in the world. The stars would go out, galaxies hit each other. It's possible that the end of time will happen while you only watch hours go by. This idea formed the emotional core of Interstellar. In that movie, a crew lands on a planet orbiting close to a black hole. Due to extreme time dilation, every hour spent on the surface equals 7 years back on Earth. That's not exaggeration, it's math. The physics consultants on the film, including Kip Thorne, made sure the black hole's gravity matched Einstein's predictions. And yeah, it made people cry for a reason. Time isn't just a background rhythm, it's part of the geometry of the universe, and that geometry changes. Black holes stretch space-time so intensely that they practically bring time to a standstill, at least from a distance. What will happen if someone does cross the event horizon? From the outside, it looks like they never do. It looks like they freeze, fade, and redshift away. From their point of view, though, they fall right in, fast, without a choice, and forever. There is no wall to be seen, no interesting border. It was just a smooth fall into darkness, and time outside seemed to go by much faster. And what's at the center of that black hole? A singularity, a point where density becomes infinite, and space-time completely breaks down. The laws of physics as we know them no longer apply. Time, space, energy, none of it behaves normally. It's not just that time gets weird there, it may cease to exist altogether. GPS and time offsets, how satellites prove Einstein, right every day. You use more than just a location service when you use Google Maps or call an Uber. Dozens of satellites 20,000 kilometers above Earth are being asked to do a small wonder. Your phone can tell how long each signal took to arrive because these satellites send time-stamped messages down to it. With that information, it figures out exactly where you are. That's how GPS works. The really interesting part is that none of this would be possible without Einstein's theory of relativity. The GPS satellites move very quickly. They go about 14,000 kilometers per h. It's also very far from Earth's surface, so the gravity isn't as strong there. Einstein said that both of those things change the course of time. Because of their speed, special relativity dilates time, which slows down their clocks. But since they are in a place with less gravity, time slows down, making their clocks tick faster. When you put them together, guess what? In the end, this means that the clock on each GPS satellite runs about 38 microseconds faster every day than a clock on Earth that is the same. You might be thinking, so what, that's barely anything. But in GPS time, that's a disaster. Light travels about 300,000 kilometers per second. In just 1 microsecond, that's a 300-meter error. After a single day, if left uncorrected, GPS positions would be off by 10 kilometers. That means your Uber could drop you off in the next town, or in a lake. To fix this, engineers actually pre-adjust the satellite clocks before launch. Their tick rate is deliberately slowed, so that once they're in orbit and affected by relativity, they tick at Earth speed. It's like building a watch that's intentionally broken, so it works perfectly once you throw it into space. If that sounds insane, well, welcome to modern physics. So here we are, GPS, something billions of people use daily, silently confirming Einstein's predictions with every turn and traffic reroute. It's one of the rare times in science where something so abstract, time warps in space, has such a direct everyday impact on your life. But it doesn't stop with positioning. Satellite communication, banking systems, military operations, and even stock exchanges rely on ultra-precise timing. These networks are synchronized using GPS time, which is corrected for relativistic effects. Without those corrections, digital infrastructure would desync, causing chaos across every global system that runs on a clock. This entire phenomenon has forced physicists and engineers to stop treating time as a constant. Time has become something we tune, like an instrument. We tweak it depending on where it is and how fast it's going. GPS clocks are constantly being monitored and recalibrated, not because they're faulty, but because the universe itself doesn't play fair with time. It also changes what a second means. Atomic clocks measure the frequency of shaking of cesium atoms, which is what a second is based on. But the spot of that clock is important. The atomic clock will tick at different times if you put it in space or move it up a mountain. The same atoms. A different view of time. So we need to put our data in the right context. Earth-based time, satellite time, and universal time. It really is all relative. The strange fact is that the more we learn about time, the less we believe it exists the way we thought it did. It's not a single beat that everyone hears. People in the area tell it in different ways based on the speed and gravity. Every second, GPS shows it by not being in line. This also means there's no such thing as now across the universe. There's only now here. Now on a GPS satellite is slightly ahead of now on Earth. Now near a black hole? Who knows? Time is smeared out, bent, wobbled by the shape of space-time around it. Take a moment to think about what just happened the next time your phone tells you you've arrived at your destination. Thanks to one of the strangest ideas in physics, a group of satellites, each ticking at a slightly different rate, just worked together to find you. To do it, they had to bend time. Einstein's ideas are not just scribbles on a blackboard or high-tech, futuristic stuff. They are part of the world you live in. Time is weird, time is twisted, and time as you know it is a beautiful lie. The world makes this clear every time you open your Maps app. The twin paradox, aging at different rates in the same universe. Think about this. Two exact twins. We'll call them Kai and Leo. They live together, eat the same food, and watch a lot of the same shows. But one day, Kai becomes an astronaut and goes into space almost as fast as light. Years go by. Kai then comes back to Earth and gets off the ship. Leo is shocked to see that his twin hasn't aged nearly as much as he thought. Leo is old, has grey hair, and lines from living a long time. Kai? Almost the same as the day he left. That's not made-up science fiction. That is Einstein's twin paradox, and it is one of the most strange and real effects of relativity. In Einstein's special relativity, the faster you move through space, the slower you move through time. So when Kai zooms off into space at incredible speeds, his biological clock slows down compared to Leo's. Every heartbeat, every blink, every cell division takes longer. But to Kai, it doesn't feel slow. He lives out his mission as normal. Reads, sleeps, works out, drinks coffee in low gravity. Time feels normal to him. But back on Earth, time is racing ahead. This is where people mess up. From Kai's point of view, couldn't he say that Leo was the one leaving? Leo should be the one who ages more slowly, right? That's the strange thing about it. But speeding things up is the answer. To get back home, Kai had to shoot rockets, change direction, and slow down. That doesn't make sense. Leo stayed in an inertial frame, which means it didn't move or speed up. Kai wasn't. Because of that speeding up, Kai's view of time is the one that is most different. This isn't just a thought experiment. Scientists have actually tested time dilation with twins, just not humans, yet. In 1971, the Haffel-Keating experiment flew atomic clocks on commercial airliners around the world, comparing them to clocks that stayed on the ground. The result? The airborne clocks came back with slightly less time logged, just like Chi, just like the paradox predicted, and it gets even more real with GPS. Those satellites in orbit. Their onboard clocks tick differently than Earth-based clocks, not just from gravity, but from speed. Engineers correct for that using relativity. Without those adjustments, GPS wouldn't work. Einstein's math is baked into your directions to the grocery store. The twin conundrum is more than just clocks and circles, though. It changes the way we think about what is fair. It seems like two people could live in the same world, go on different paths, and still be biologically different. They didn't do anything wrong, so how come one aged faster than the other? It looks and feels like lying. But that's because our brains are still set up to think of time as fixed, like it's always the same for everyone. It's not. Time is a dimension, and like space, you can travel through it differently depending on your path. Think of a flat map with two cities. One person takes a straight road, another takes a winding detour. Both start and end in the same place, but the lengths of their journeys are different. Time is like that too. It's just not visible to us, but relativity shows it's there. Think about what this means for space travel that lasts a long time. Let's say that people build ships that can move at a speed that is much slower than light. Someone could leave Earth, go to a faraway star system, and come back to find their grandkids grown up or gone. It seemed like a long time to them. To Earth, it took a very long time. It's not just a curiosity, it's a warning. If we ever become a spacefaring civilization, we'll have to rethink what time means. We'll need new ways to track it, to coordinate it, to emotionally cope with what it does to relationships. "I'll be back soon" might mean one thing to the traveler, and something very different to the people waiting. There's also something deep here, though. Time isn't a running clock, as the twin paradox shows. It's about you. Your direction, speed, and gravity all play a role. That one person's experience is wrong is not the point. That time doesn't work for everyone. The event horizon. Freeze. Why time stops at a black hole's edge. Imagine that a rocket is slowly moving toward the edge of a black hole. There is no big drop. It's just floating in quiet. You're far away where space is quiet and gravity is cool, so you can watch it safely. But something odd takes place. When the ship gets close to the event horizon, which is the edge of the black hole, it slows down. Not in terms of speed, but of time. You continue to look. It gets less bright, more red, fainter. After that, it stops moving at the very edge, never going across, never going away, just stuck in a strange limbo. It looks like time has stopped to you. Also, in a way, it has. This is one of the strangest and most real things about general relativity. It's not a wall that the event horizon is. There's no light, flashing, or loud "don't enter" sign. It's just the line that can't be seen where flight is impossible. From the outside, though, something strange takes place. Time itself is pulled apart. As an object gets closer to a black hole, gravitational time dilation kicks in. The intense warping of space-time makes time tick slower near the black hole than farther away. From the traveler's perspective, say the astronaut on that ship, everything seems normal. Their heart beats, their watch ticks, their thoughts move forward. They might feel the ship rocking, might hear the engine hum. But to you, watching from afar, those heartbeats take longer and longer until they barely happen at all. This illusion is so strong that to a distant observer, the astronaut never actually crosses the event horizon. Instead, they appear to slow to a crawl and freeze just above the edge. It's not because they're stopped, it's because the light carrying their image takes longer and longer to reach you. As they fall deeper into the gravitational well, their light gets stretched, redshifted, into lower and lower energies. Eventually, it becomes undetectable. They fade out like a ghost, not with a bang, but with a slow dissolve. This isn't just theory, it's baked into Einstein's equations. The closer you get to the event horizon, the more extreme the time dilation becomes. Right at the edge, time stretches to infinity. That means, from your point of view, someone falling in would take forever to reach the horizon. You'd die of old age, the Earth would fade, stars would burn out, and that ship would still be hovering there, frozen in time. Remember though, that's just what you see. When someone falls in, there is no freeze frame, not a slowdown. They can't find any time warps. In real time, they sail past the event horizon, not any sounds. There was no quick stop. There was only a quiet, one-way fall into what comes next. And once they're past that limit, there is no way for them to get back. Not even a Snapchat story. This dual perspective is what makes black holes so trippy. Two truths can exist at once. The outside observer sees time stop. The falling observer sees time flow normally. Both are right, depending on their frame of reference. Some experts say this border is so strong that it erases memories from the beginning of time. When something goes into a black hole, it is hidden from the rest of the world. Not only physically, but also in terms of time. Their timeline gets stuck just above the edge, making it impossible to reach. This is where things get really serious. What changes about how you see the outside world as you fall in if time stops for everyone else at the event horizon? Relativity says that the rest of the universe seems to be moving faster. It would make galaxies spin faster. In an instant, civilizations would rise and fall. In the last few seconds, before you hit the horizon, you might see the whole future of the world happen very quickly. Take a look at that. The world around you ticks 1 billion times faster than your clock. In one last look, you could see the stars die, the Milky Way crash into Andromeda, and even the end of the universe's heat death. That's the reason black holes aren't just things. They take you back in time. You can't run away from them or ride them into the past. These are places where time bends so hard that it splits into different versions based on who looks at it. No time in light speed, the photon's timeless journey. You turn on a flashlight. There is a beam that cuts through the darkness. Photons, those bits of light, are now going in a straight line across space. Some may go for seconds, while others may go for millions or even billions of years before they hit something, like a wall, an eyeball, a planet, or a camera. The crazy thing is that the trip didn't take any photons at all. From their point of view, it happened right away. Not a second, not a moment, right there. Photons, unlike you and me, move at the speed of light, which is the fastest speed that anything can go. And relativity says that things move through time more slowly as they move faster. When you speed something up to the speed of light, time stops. The ideas of before and after don't exist for a photon. It doesn't go through time. It only exists at its starting point and ending point. That beam of sunlight warming your skin, each photon was emitted from the sun's surface roughly 8 minutes ago from your perspective. But from the photon's perspective, if it had one, it left the sun and hit your skin at the same moment. Emission and absorption are simultaneous events in its timeline. Because we think of time in terms of steps, this idea hurts our minds. We move forward, we take deep breaths, we get older, we do everything one moment at a time. Moments don't work for photons though. They're too far away for clocks to reach. In physics terms, we describe this using something called proper time, the time measured by an object in its own frame of reference. A stationary clock ticks at full speed. A fast-moving one ticks slower. A photon, its proper time is 0. It lives in a state where the beginning and end of its journey are collapsed into one. That's not just a figure of speech, it's math. The time and space between two events is defined by relativity. That gap is equal to 0 for something going at the speed of light. The photon doesn't move through space and time. It just exists on a null line, linking places without being affected by them. That's why light can do such strange things. Photons mess with each other in quantum physics. Their paths can be changed at the same time. In between being taken and not being absorbed, they can be. Just because their timeline is kind of flat, they don't go through passing. They can act like particles, waves, and paradoxes, so there is nothing stopping them. This also raises weird questions about causality. If photons don't live through time, how can they carry information from one place to another? How do they cause effects if they don't experience change? They do not need to. That is the truth. Indeed, the universe is designed for people who can see it from below the speed of light. We can see how things happen because we have time. The photon doesn't tell a story, it just joins 2 points together. Things that we think of as moving are really just the universe's way of connecting events using the only thing that can get from one to the other without time: light. Just picture this happening out in space. From our point of view, some photons have been moving for 13.8 billion years, which is how long it took for the cosmic microwave background to start emitted. They've gone around black holes, crossed growing galaxies, and gone around dying stars. But for them, it's been nothing. Just go from A to B snap. This is why, when we look at distant galaxies, we're really looking back in time. Those photons left their source long ago, and we're only catching up to them now. But they never felt old. They were ageless the whole way through. The concept of time simply doesn't apply to light the way it applies to matter. Photons don't age, they don't remember, they don't wait to arrive. That's why, in a universe full of ticking clocks and shifting matter, light feels like something alien. It's the ultimate spy, moving everywhere, yet experiencing nothing. Block universe theory: all moments exist at once. This text is being read by you. This one now, this one now. It seems like time is moving faster, right? 1 second, then the next, and so on. What if, though, that flow is just a trick? What if every moment, now in the past or in the future, is always there? Time doesn't move is what the block universe theory is all about. There is only one thing. In this view, the universe is like a 4-dimensional block, 3 dimensions of space, 1 of time. But instead of time being a river that flows from past to future, it's more like the vertical axis on a graph. All moments are equally real. The moment of your birth still exists. The moment you first fell in love. It's not gone, it's just sitting on another part of the block. The end of your life? Already there. Waiting, etched into the fabric of space-time like every other point. Einstein's equations actually hint at this. In special relativity, there's no absolute now. 2 observers moving at different speeds can disagree on whether events happened at the same time. That means simultaneity is relative. What's happening right now for you might already be in the past or the future for someone else. And if that's true, then maybe now isn't a special slice at all. Maybe it's just one of countless slices in a giant loaf of reality. In the block universe, the entire timeline of the cosmos exists like a sculpture, not being created as we go, but already fully formed. Time, in this model, is more like space. You wouldn't say that one location is more real than another, just because you happen to be standing there. Same goes for moments in time. You're just currently located at a particular temporal address. But if that's true, then what the hell are we going through? That's where things get tough. Some scientists and philosophers say that the idea that time is moving, or moving now, is just an illusion of the mind. Your brain is working on memories, making guesses about what will happen, and matching your heartbeat to patterns. It's putting together one moment at a time to tell the story of time. But outside your head, there's no story. A schedule is all that's there. Julian Barber, who we mentioned earlier, takes it even further. He believes time doesn't even exist, just configurations of the universe, snapshots he calls nows. According to him, there's no flow, no motion, no before or after, just a vast set of possible universes, each frozen, existing in a kind of timeless platonic realm. And what you feel as passing time is your consciousness leaping from one now to another, creating the illusion of continuity. But the block universe isn't just philosophy. It has serious implications for physics. In this model, the equations of motion don't evolve over time. They describe the entire timeline at once. General relativity, in particular, treats space-time as a fixed structure. The past doesn't disappear. The future isn't unformed. It's all just there. This also makes me think about fate and free will in a bad way. Does the fact that the future is already written in the block mean that everything is set in stone? Are you just following a script that's been set in stone in space-time? There are scientists who say yes. Some people say that your choices are part of the block, but you still own them, just like you own where you live. You're not a doll. You're just taking a picture of a very detailed plan. The block universe changes the way we think about death, which is a creepy effect. As people have always thought, people come and go, they come and go. But no one really goes away in the block view. It's still possible to see their whole history, but not where you are now. It gives me some comfort in my life. In that block, every moment you had with someone you've lost is still there. You're not in that part of the universe anymore. The block universe theory isn't universally accepted. Some argue it doesn't explain entropy, or why we remember the past, but not the future. Others say it's just a mathematical trick, useful for physics, but not the full story. Still, it challenges the deepest assumptions we carry about time. The arrow of time entropy's cosmic march. You break a glass, it breaks into 1,000 pieces. But have you ever seen a piece of broken glass jump off the ground and put itself back together? Not at all. You will never do that. The reason for this is that time, at least the way we see it, only goes forward. The arrow of time is the name of this one-way street that has nothing to do with clocks. It's all about entropy. Entropy is a measure of disorder. The more random and chaotic a system is, the higher its entropy. A tidy room, low entropy. A messy one with clothes everywhere and food wrappers under the bed. High entropy. And according to the second law of thermodynamics, the total entropy of a closed system, like the universe, can never decrease. It always increases or stays the same. Translation: the universe is getting messier over time. That's the real reason you remember the past, but not the future. Not because of your brain, not because of memory, but because the past had less entropy than the future. It was more ordered, and every process you've ever seen, from rotting fruit to stars burning out, is part of that grand shift from order to chaos. The direction of time is the direction in which entropy increases. But it's kind of strange because the basic rules of physics don't care about the way of time. Move, gravity, and electromagnetic fields all have models that can be used both forward and backward. Newton's rules still make sense if you watch two planets circle each other backwards. If you turned a movie of particles moving around in a box around, there would be no math that would tell you it was wrong. That being said, why does chaos get to break the balance? Why is that the law that says what an arrow is? The truth is that not everyone knows for sure. We do know that the entropy of the early universe was very low. There was a lot of matter and energy right after the Big Bang, but they were very well organized. Time moves in a certain way because of that low entropy start. Since that point of origin, the universe has been slowly growing, cooling, and spreading out as it moves toward greater disorder. Just picture the universe as a deck of cards that has been neatly mixed up. But it's getting more and more mixed up over time. We always move from the past to the future, because things don't just get put back together on their own. Your entire life is built on this principle. You age because cells break down and lose structure. You remember breakfast because your brain stored the memory after it happened, not before. Heat flows from hot to cold, never the reverse. All because the universe is running down the clock of order. This is also why you can't unburn toast, unmix cream from coffee, or unsneeze into silence. Entropy has a direction, and that direction defines time as we know it. But now things get scary. If the world's low entropy start is what made time's arrow, then what made that start possible? Ask yourself why the universe began in such a neat state. That is still one of the most puzzling problems in physics. Some ideas say the Big Bang wasn't really the beginning, but rather a bounce from an earlier world. Some people think that time might go backwards in the very far future, when entropy is at its highest and there is no other way to go but backwards. Entropy is what makes the present moment possible. In the end, the stars will burn out and leave the sky dark. Your grandparents were younger than you are now, and your coffee will cool down. We don't get the direction of time from the universe. It is what we come into, being born into a time with less chaos than the next. You can't see that line, but you can feel it all the time. Every time my heart beats, every movement. It's always sunrise to sunset, and never the other way around. Why entropy drives time's illusion. It feels like time is real. You get up, eat, work, and get older. Things take place in a certain order. Memories form in the past, and options appear in the present. Yet, here's the crazy twist. What we call time might not even be a basic part of the world. That could just be a result of entropy rising, or the start of more chaos. That is, time might just be a trick, and entropy is the con artist behind it. Let's strip it down. The second law of thermodynamics says entropy, the measure of disorder, always increases in a closed system. In practical terms, this means the universe is constantly moving from neat to messy, from structured to chaotic. Ice melts, buildings crumble, suns burn out. Every tick of time is marked by things falling apart just a little more than before. But here's the kicker. Entropy is the only law of physics that cares about direction. Every other fundamental law, gravity, electromagnetism, quantum mechanics, works just fine backward. Run them in reverse, and nothing breaks. The math is symmetrical. The laws don't know or care if time is moving forward or back. If you feel that way, where does it come from? It's all just chaos. Your brain remembers states with less chaos, which makes you feel like time is going faster. You remember breaking the egg, not the shell suddenly coming back together. You remember the party before you had to clean up. The line that decay draws is what your memories are made of. Your body, your mind, and even your attitude change along this path of growing chaos. Now picture the world frozen at maximum entropy. In this state, nothing can change because everything is already the most disorganized it can be. There is no movement, friction, change in temperature, creation of new stars, or collapse of galaxies. Time would not mean anything in that world. When nothing changes, you can't tell the difference between before and after. That's what makes entropy so powerful. It's not just a trend, it's the thing that gives time its rhythm. When entropy increases, we say time has passed. But without that increase, there's no clock, no tick, just stillness. Some scientists argue this means time isn't a basic ingredient of the cosmos. Instead, it's an emergent property, like how wetness comes from lots of water molecules or temperature comes from billions of tiny motions. Time might just be what you feel when the universe is busy rearranging itself into more chaotic forms. It means time might not be a river we're flowing through, but a way of organizing changes in the landscape around us. As entropy rises, we label that change the future. As entropy decreases, which it never does, we'd call that the past. But in the grand equation of the universe, those labels are meaningless. They're just bookmarks in a disordered story. This also sheds light on why we remember the past but not the future. Your memories are low entropy imprints. You encode them as your brain moves from a clean signal to a more scrambled one. There's no mechanism for building memories from higher to lower entropy. That's why we always remember one direction only. The illusion of time lives in the direction entropy lets us recall. Entropy is in charge even in the study of the universe. It was surprising how low the entropy was in the early world, right after the Big Bang. Yes, it was hot and thick, but it was also very regular, easily guessed. Time moved in a certain way because of that rare rule. Since then, the universe has been getting more complicated, with stars growing and dying, planets coming together, and black holes absorbing light. Each of those changes moves things farther away from the start with low entropy. There is a tick of time in everything. And if you're wondering why time feels so steady, why each second feels like the last, it's because entropy increases steadily enough on human scales. But zoom out, and time gets stretchy. Around black holes, in quantum fields, during cosmic inflation, time loses its shape. Why? Because the rules entropy plays by starting breaking down or warping under pressure. What does this mean for us? This means that your whole life, the series of moments that seem so real, might just be your mind riding the rise of rising chaos. The big universal clock isn't beating. There is no clear present, past, or future. There is only a world that is always falling apart, and a species whose brains are wired to see that falling apart as time. Reversible laws, irreversible universe. When you watch a video of two pool balls hitting each other backwards, you wouldn't be able to tell the difference. When you move the balls backwards, they spin, roll, and split, just like when you move them forward. To explain this, we can say that Newton's rules, quantum mechanics, and even the equations of general relativity don't care which way time moves. They are equal in time. But what's real? The place where you live? Without a doubt, it does care. Glasses break in real life, but they don't get back together. Fires burn wood, but ash never comes back together. So, what's going on? How is it that the rules that govern the universe can be turned around, but the universe itself can't? Once more, the answer lies in chaos and scale. Particles behave in ways that can be completely turned around at the tiny level. It makes sense for an atom to bounce off a wall in both forward and backward directions. According to quantum physics, time reversal symmetry is true in systems that are completely separate from each other. But when you zoom out and see trillions of particles reacting with each other, you see something that can't be turned back. Time moves forward. Let's say you open a perfume bottle in a sealed room. The molecules spread out naturally. They diffuse from a concentrated cloud into a wide, evenly distributed scent. That's entropy rising. Could the molecules technically all cluster back into the bottle? Sure. The laws of motion allow it. But the odds? Astronomically low. It's not impossible. It's just so statistically absurd that we say it's irreversible. There are vastly more messy configurations than ordered ones, and the universe tends to move from rare to common, from improbable to probable. This is what the paradox is all about. The rules allow for reversibility, but the results tend to support chaos. The universe is just taking chances. It's not breaking any rules. The odds are that time will go on. The way heat moves from hot to cold, the way our bodies age, and even the way stars burn through their fuel all show this. Each particle in each case has a changeable dynamics. But when they work together, they make processes that can't go backward. Even quantum mechanics, the most fundamental level we know, has time-symmetric equations. The Schrödinger equation, which governs how quantum states evolve, works just as well in reverse. But the moment you make a measurement, collapsing a wave function into a concrete outcome, irreversibility sneaks in. Suddenly, you can't uncollapse the measurement. The act of observing locks in a result and cuts off the path backward. Some physicists believe this is where time's arrow is born, not in the particles themselves, but in the act of measurement, in the process of observation. Once information is gained, it can't be ungained. The system has changed, and with it, so has time. Some say it's all about losing information. Even if you burn a book, the molecules are still there. All of the atoms have been found, but the words, their meanings, and their order are gone. A state has low entropy because it has a lot of knowledge. If you lose it, you're one step closer to chaos. You can't take that step back. This contradiction between reversible laws and irreversible experience is one of the biggest puzzles in physics. It's like the universe speaks two languages, one elegant and timeless, the other messy and directional, and somehow we live at the intersection. The microscopic world is like individual musicians, each capable of playing notes forward or backward. But when they all play together, the symphony only goes one way. That's the power of scale, and that's the illusion of time. Your heartbeat, your memories, your sense of past and future, all of it emerges not because time flows, but because the universe doesn't bother to rewind. It doesn't need to. Statistically, it's easier to go forward. Cosmic inflation and temporal disruption. Let's go back in time not just a few billion years, but all the way to the very first second after the Big Bang. 1/trillionth of a second is how short this moment is. It's so short that a blink seems like a lifetime. And the world didn't grow slowly at that moment. It grew very big. At the speed of light, it grew from the size of an atom to that of a star. It didn't just make space bigger, it also broke every rule we thought we knew about time. This is called cosmic inflation. Cosmic inflation is one of the wildest ideas in modern cosmology. It was proposed to fix a few major problems in Big Bang theory. For example, why is the universe so smooth? Why does it look the same in every direction, even though light wouldn't have had time to even out those differences? Why is space so flat, like a perfectly ironed bedsheet? Inflation solves all of this by saying, right after the Big Bang, the universe went through an insane growth spurt, expanding faster than the speed of light. It wasn't just that inflation made space bigger. It also changed time so much that it was no longer recognizable. Einstein's fabric of spacetime normally connects space and time. Space grew so quickly during inflation, though, that time couldn't keep up. There is no longer the normal link between cause and effect, between before and after. In fact, the term before inflation might not mean anything. There may not be a before. Prices going up could be the real start of what we call time. The way we think about time only makes sense when the universe's shape is fixed. When things like watches can tick, energy spreads out and particles form. But when prices went up, that wasn't happening yet. Space was made up of nothing but energy, pushed along by a strange field called the inflaton field that didn't have any particles, a temperature, or a meaningful clock. Everything seemed to be stopping, but it was actually getting bigger faster than ever. Because of this, one of the scariest ideas in physics comes to mind. Maybe there was no time before inflation. It's not that we can't see that far back. There was never a back. There wasn't enough inflation. It's possible that time began in inflation, which happened when the universe cooled down and started to take shape. Picture a balloon. At first, it folded up very tightly. Then all of a sudden, it grows bigger in every direction. If the rubber on that balloon had a clock built into it, the clock wouldn't start to tick until the balloon hit a stable shape. That's what the world could have done. Time had no meaning until inflation stopped. Now fast forward. Inflation ends. The universe settles down, particles form, atoms bond, stars ignite. Finally, time as we know it begins to flow. But that flow is forever shaped by inflation's opening act. The uniformity of space, the flatness of geometry, the seeds of galaxy clusters, all of it came from that unmeasurable, untouchable moment. What's really wild is that inflation might have created pockets of spacetime that each became their own universes. In some theories, inflation doesn't stop everywhere at once. It stops in bubbles. Each bubble becomes a universe with its own laws, its own constants, its own arrow of time. This is called eternal inflation, and it suggests that our universe is just one tiny pocket in a multiverse filled with others. And in each of those pockets, the flow of time could change, or it could stop. Cosmic inflation did more than just make stars and galaxies possible. It pointed the arrow of time in the right direction. That made it possible for entropy to start rising. Before that, not any clocks, not moving, not a cause and a result. So much quantum chaos that it stretched out until time could be born. This flips everything. Time isn't something that came first. It might be something that emerged after the universe figured out how to cool down. Before inflation, there may have been no before, just a timeless, formless sea of potential. And we only know this because of the marks that inflation left behind. Tiny waves in the cosmic microwave background, which is like a picture of the universe when it was young. These waves show us where quantum fluctuations were stretched out across space during expansion and then stopped moving. Eventually, these fluctuations turned into stars, galaxies, and us. Time before the Big Bang. Does it even make sense? We're used to things starting off, the beginning of your favorite song, your coffee starts to make. The idea of the Big Bang says that everything had a beginning. The next question is really hard to answer. What happened before the Big Bang? Was there a time before? Was there time? Or are we asking a question that doesn't make any sense? No, the Big Bang wasn't a blast in space. It was the beginning of time and space itself. General relativity says that if you go back in time through an expanding universe, you will eventually reach the singularity, which is a point with an infinitely high density. There comes a time when math doesn't work, physics doesn't work, and time as we know it hits a wall. Not a dead end, but a place where our ideas don't work anymore. You could compare this question to the question, what's north of the North Pole? The question is based on a structure that might not even be there. But scientists don't like to give up. Even when time seems to be running out, they don't like giving up. They started to look deeper, using quantum gravity, loop theory, and string theory to try to see what was going on. One idea is that time didn't start with the Big Bang, but rather it moved around. The Big Bounce idea is based on this. Instead of a singularity, the universe might have gone through a time of contraction before it began to grow again. Time never ends in that model. The Big Bang wasn't the start of anything. It was just a starting point. It looks like the bottom of a space trampoline. Another theory comes from loop quantum gravity, where space and time are made of discrete chunks, kind of like pixels. When the universe gets too small, those pixels push back, preventing a true singularity. The result? A rebound, a pre-Big Bang universe that shrinks, pauses, then gives rise to ours. Then there's string theory, where the fundamental building blocks of reality aren't particles, but vibrating strings. In some versions of string theory, our universe is a three-dimensional brain, floating in a higher dimensional space. The Big Bang may have been caused by two brains colliding. If so, time could exist outside our universe, in the bulk space between brains. That means time didn't begin with us. We're just a tiny chapter in a much bigger book. There's also a different view. Time is not basic, it emerges. In some models, what we think of as time doesn't happen until certain conditions are met, like when the temperature, space, or entropy are just right. Those things might not have been true before the Big Bang. Not a particle, no talking to anyone, not any clocks, nothing ticks if there is no change or chaos. In other words, time wasn't there to begin with. It wasn't important yet. And then there's imaginary time, an idea proposed by Stephen Hawking. In this model, time near the Big Bang behaves like a spatial dimension. No edges, no boundaries, just a smooth, rounded surface, like the surface of a sphere. Hawking argued that the universe didn't need a starting point because imaginary time makes the beginning look like the South Pole, finite, but with no before. Some physicists say, hold up, maybe our obsession with before is a cognitive glitch. Our brains evolved in a world where every effect has a cause, where every event follows another. But that might not apply at the origin of the universe. Time may not just be curved, it may not be applicable. Yet the mystery remains seductive. If there was a before, did it have its own laws? Was it chaotic, or empty, or something we don't even have words for? Did other universes come and go in a cycle we'll never see? Or was time itself born in that initial burst of cosmic inflation? We might never know for sure. We can only see so far into the cosmic microwave background, which is the oldest light we can see. After that, there is darkness. Not because there is no light, but because time is running out. So take a moment the next time you look up at the stars and wonder what came before. You might be going beyond what time can handle. The rules that decide before and after might not have been around yet. The Big Bang wasn't just the start of everything. From that point on, things got better. The start of before. Loop quantum gravity, a timeless structure of space-time. The time goes by. We believe that. The minutes and seconds add up, and the future moves quickly toward us. But loop quantum gravity, one of the most daring ideas in modern physics, says that sound might just be a dream. Time doesn't exist in this system. Not really at all. Not below the top. Because of something else. It's not a river or a thread. As a dream. Loop quantum gravity, LQG, is a theory that tries to do what Einstein couldn't: merge general relativity with quantum mechanics. Gravity, in Einstein's world, is geometry, the bending of spacetime by mass. But quantum mechanics sees the world in particles, fields, and probabilities. These two descriptions don't play well together. At cosmic scales, general relativity is king. At atomic scales, quantum rules. So what happens when you need both, say near a black hole or at the birth of the universe? In this case, loop quantum gravity comes in. Quantize reality is what it tries to do. LQG says that space is made up of tiny loops, which are separate chunks of volume, just like matter is made up of atoms. They are like the atoms of space. It's hard to believe how small they are, only 10 to 35 meters across. A proton is a lot bigger than this. It is made up of these loops that make up an unseen web we call spin networks. The way this web changes over what we call time is called a spin foam. In LQG, time isn't part of the fundamental equations. It doesn't even show up. The theory is built to describe how space changes from one state to another, but it doesn't do it over time. It does it through relationships. The network of loops transforms, but not according to a cosmic clock. Instead, events are defined by how parts of the network relate to each other. No ticking, no sequence, just structure. This idea challenges our most basic instincts. How can things change if there's no time for them to change in? The answer is that change in loop quantum gravity is relational. It's not about time passing, it's about how different configurations of space link together. Time, in this model, emerges only when observers, like us, look at the system and impose a sequence on it. Think about reading a flipbook. When you look at still pictures, your brain thinks they are moving. They're not moving though. You're. The world may also be a frozen web of connections in the same way. Our minds are made up of patterns that have evolved to expect that one thing will lead to another. These patterns connect these frozen states into a story we call time. Physicist Carlo Rovelli, one of the leading figures in loop quantum gravity, puts it like this: time is not a universal variable. It's an approximate concept that only makes sense under certain conditions. He compares the absence of time in fundamental physics to the absence of heat in individual molecules. No single molecule is hot. Heat is what you get when trillions of them jiggle around. Time might be like that, not real by itself, but something that arises from the collective dance of quantum loops. LQG also has something to say about the Big Bang. In standard general relativity, the universe begins with a singularity, an infinitely small, dense point where the math breaks. But in loop quantum gravity, the granularity of space prevents that singularity. Instead, the universe bounces. There's a minimum volume, a smallest possible size, beyond which it can't shrink. Before the Big Bang, there was something, a previous phase, maybe even a collapsing universe that rebounded into ours. Still, there's no time. In these models, before and after are just words that describe when one spin network changes into another. There's no main clock, no way to go, it's just links. Some people say this makes it hard to test the idea. How can you make predictions without a clock to test your ideas against? How can you be sure? That's a good question. LQG isn't finished yet, and it's just one of many ideas that are trying to be the first quantum theory of gravity. But it does present a strong challenge. The thought that our core belief that time exists may be completely false. String theory without time. String theory is one of the most bold and divisive ideas in all of physics. What is its goal? To bring all of these things together, gravity, quantum physics, and the natural forces, under one beautiful moving roof. String theory says that the smallest parts of the world are not particles, but strings, which are very small loops of vibrating energy. Atoms, quarks, and even gravity are all made up of different types of vibrations. It looks lovely, it's very big, it has up to 11 dimensions. Here's the catch though. Time doesn't exist in many forms of string theory. String theory doesn't just follow the rules, it tries to change them. Time is not a basic part of mathematics. It often shows up as something that happens along the way. In other words, it's not something that is built into reality. It's more like a result, or something that only shows up when certain big picture conditions are met, like the weather or a rainbow. It seems real. It seems real. It's only there because of the bigger picture, though. Some string models, particularly those tied to M-theory and ADES-CFT correspondence, suggest the universe can be described completely without reference to time. In these frameworks, you can describe everything, space, energy, even black holes, using pure geometry or quantum information. Time is just not needed in the equations. This means a lot of things. Take the ADES-CFT correspondence, which is a strong pair that scientist Juan Maldacena came up with. It means that a universe with gravity like ours can be exactly mapped to a universe with less gravity, in a way that's a lot like an image. And in that version with fewer dimensions, the description doesn't always need time to work. On a surface that will never change, the past of the whole world can be stored. To put it another way, the flow of time inside the world could just be an illusion, a trick that a machine plays on you because it doesn't actually feel time. There are many possible worlds in string theory's landscape, and in some of them, the rules of physics might not even apply and time might not even exist. How would it feel to live in a place like that? Could there even be awareness without memory or order? We don't know. But string theory makes it possible. Now, this doesn't mean time is a lie in your everyday life. Obviously, you still age. You still catch buses, miss deadlines, feel Monday drag longer than Friday. Time works at our scale. But what string theory suggests is that this experience of time might not be a feature of reality. It might be an emergent property of the way large systems of strings interact. Think of waves in the ocean. The ocean doesn't need waves. But when energy flows through it, the surface ripples. Maybe time is like that, a ripple in something deeper, something timeless. What about the Big Bang? String theory doesn't use the standard singularity at all. There is no point where everything breaks down because strings have length. The universe may have started out hot and thick, but there was no hard start. Some models even say that the world existed before the Big Bang, but there was no time as we know it. It might not have been a moving clock leading to a moment of creation, but rather a change between endless stages, a restart, a changed state for string vibrations. One of the strangest consequences of time-free string theory is what it says about cause and effect. If time isn't fundamental, then causality, our idea that one thing leads to another, might also be emergent. This doesn't break the universe, it just means that cause and effect might only make sense after time emerges, not before. What do we still have? A picture of the world that makes us feel small in every way. Time, which is the stage we play on and the beat of our lives, could just be a plot made up of strings. The real rules could be made in a different time. Be quiet, eternal and fixed. The Planck time limit, where time breaks down. You know about a second. You know what a moment is. But what about the quickest tick of time? That moment is so small that it's not only quick, it's really important. It's called Planck time, and it's not just very short. It's the tiniest piece of time that makes sense in the world. Have you tried to look inside it? The rules of physics don't work anymore. Reality has bugs. Time stops making sense. So how short is it? Planck time equals about 5.39 x 1044 seconds. That's a decimal point followed by 43 zeros, and then a 5. It's the amount of time it takes light to travel one Planck length, the smallest meaningful length in physics. Think of it as the pixel size of the universe's time dimension. Below that, there's no frame to grab, no before and after. Just quantum foam, chaotic, structureless, unknowable. Where does this number come from? It's derived from three constants: the speed of light, c, the gravitational constant, g, and Planck's constant, h. Put them together just right, and you get the Planck time. It's the point at which our best theories, general relativity and quantum mechanics, start throwing errors. Like dividing by zero, physics just stops making sense. What's the big deal about that? Planck time is right on the edge of the Big Bang. The Planck era is the first Planck time after the beginning of the world. It is reached by going back in time and drawing a line. Before that, we have no idea what took place. Our math doesn't work that way. There is a wall in time, but not because it hides something. There may not have been a wall in time at all. Think about using a yardstick to try to measure an atom. Not only is it the wrong tool, but the question itself doesn't make sense. That's how it feels to try to see inside Planck time. It's not just very small, it's past the point where space and time act like smooth dimensions. At that level, reality isn't smooth. It's foamy, random, unstable. Physicists call this the quantum foam, a roiling sea of tiny fluctuations in space-time itself. Time isn't flowing here. It's flickering, bubbling in and out of possibility. Up becomes down, cause and effect become meaningless. There's no sequence, no logic, just noise. If we want to make sense of this zone, we'll need a quantum theory of gravity, something that combines Einstein's smooth space-time with the jittery chaos of quantum mechanics. Loop quantum gravity, string theory, and other radical ideas try to reach into this realm. But so far, no theory has cracked it fully. The Planck time is still a locked door. The crazy part is that time might not be essential at all if it doesn't exist at the Planck scale. It could be something that only shows up when a lot of things combine on a bigger scale. That is, until you zoom out, time might not be real. Some scientists say that the world doesn't happen 1 second at a time, but instead is made up of separate moments, like movie frames. The smallest frame that could be made is the Planck time. You can't skip between them. Don't split them up anymore. Below that, you can't have a moment. This also has consequences for our understanding of black holes. Deep in the heart of a black hole, gravity becomes so intense that space-time collapses. Near the singularity, time stretches, twists, and snaps. But maybe it doesn't hit infinity. Maybe it stops at the Planck limit, just like at the birth of the universe. A loop, a bounce, a reset. Stephen Hawking had trouble with this too. The start of time was like the South Pole of Earth, he said. You can't go further south than the South Pole. Planck time might be the South Pole of time for us. It's not just the start, it's the end. There is no before, it's not hidden, it's just not there to be found. The next time you look at your watch, keep this in mind. The tiniest tick isn't counted in seconds or milliseconds. It's based on surprise. At its core, time might not be a flow. It could be a fantasy made of pixels that is held together by something more real. Redshift and the aging universe. Take a look at the stars. Some of those stars and galaxies are so far away that their light has been moving for billions of years just to reach your eyes. But that light tells a strange story when you measure it. It's gotten longer, used up, moved more toward the red end of the scale. This is cosmic redshift. And it's not just about color. It means that time is moving more slowly in the world as a whole. When a light source moves away from you, its wavelengths stretch out, just like the sound of a siren drops in pitch as an ambulance passes by. In space, this happens on a universal scale. Galaxies are moving away from us, and their light is redshifted. But unlike that ambulance, these galaxies aren't traveling through space. They're being carried by the expansion of space itself. And as space expands, it stretches everything inside it, including the very wavelengths of light. What does this have to do with time? Plenty. Let's say a star far away explodes in a supernova, which is a very bright flash that lasts for 20 days in its own time frame. But when that light gets to us, billions of years from now, those 20 days could look like 40, 60, or even more days. The event lasts longer than expected. This is known as cosmic time dilation, and it happens because as space expands, it spreads not only light, but also the beat of time. We've seen this in action. Astronomers watching distant supernovae, especially type Ia supernovae, have measured this time stretch. The further away the explosion, the more it appears to move in slow motion. It's not because the supernova is lazy, it's because it happened so long ago, in a universe that was much younger, much smaller, and time back then was unfolding in a tighter, faster space. The deeper you look into space, the further back in time you're seeing, and the more slowed down everything appears. That's because the universe is aging, and that aging shows up as redshift. You're not just seeing galaxies farther away, you're seeing them in the past, when the universe was more compact. And that compactness meant clocks ticked differently, light moved through a denser, tighter universe, and time, as we experience it, was running on a slightly different beat. That means the light is older, not just in years, but also in terms of its beat. In the beginning, the universe was less compressed, and as it grew, time slowed down. Light moves at a certain speed, so we can only see about 13.8 billion light-years away. They are now more than 45 billion light-years away, though, because space has grown bigger. In other words, the light from those galaxies has been stretched very far, both in terms of space and time. One photon may have begun as a gamma ray with a lot of energy, but now comes as a slow radio signal. There is a story in that stretch. The world is getting older, colder, and slower. This aging has consequences. For one, it helps us map the expansion rate of the universe. The redshift of light tells us how fast galaxies are receding, and from that, we can estimate the rate at which the universe is growing. That rate, by the way, isn't slowing down. It's accelerating, thanks to something called dark energy. So the time dilation effect, it's increasing too. Eventually, light from distant galaxies will be so redshifted, so stretched in time, that it'll disappear entirely. We'll no longer see certain galaxies, not because they vanished, but because their signals can no longer reach us. It's like watching a friend walk into fog. You can wave all you want, but the fog stretches the light, the sound, the very presence until they fade out of your reality. This paints a somber picture. The further we go into the future, the more alone we become. The cosmos slows down for us, isolates us. Time, stretched by space, becomes a veil between us and the younger universe we once knew. And yet, redshift is also a gift. It lets us peer back to when galaxies were first forming, when stars were just lighting up the void, when the universe was barely a toddler. By measuring how much time has stretched, we can reconstruct a timeline of the cosmos, from that hot, dense beginning to the sprawling expanse we float in now. The heat death of the universe, when time loses meaning. Picture a world where nothing changes, not a star, not moving. There is no heat. It was just a cold, dark, and still sea that went on forever. This is not science fiction, it's the heat death of the universe, which is one of the most common ideas about what will happen in the universe after we die. It is very cold, but it's also the fact that time will pass away that makes it so scary. Right now, the universe is full of structure. Stars burn, planets spin, galaxies collide, and black holes devour everything in sight. All this happens because there's a difference between here and there, between hot and cold, dense and empty. This contrast drives change, and change is how we measure time. But entropy, the slow slide toward disorder, is always rising. Over unimaginable stretches of time, energy spreads out, stars exhaust their fuel, black holes evaporate, everything levels out. Eventually, every usable source of energy will be gone. No gradients, no engines, no chemical reactions, just particles drifting in a featureless void. This is heat death, maximum entropy, where everything is the same everywhere forever. The catch is that time can't be measured when nothing moves. Time isn't a bright line that we walk along after all. It helps you keep track of how things change. A moving clock, the Earth's spin, or the vibration of atoms can all be used to tell the time. But nothing will happen anymore in the very far future, when the last black hole has died and all matter has turned into cold radiation. Nothing has changed. Not moving. Not any clocks. There is no direction in time without change, and finally, there is no meaning. This is what makes the heat death so terrifying. It's not an explosion. It's not a catastrophe. It's silence. The universe doesn't die in fire. It fades into perfect stillness, and in that stillness, time simply stops being relevant. Events stop happening. Memory becomes impossible. Duration, sequence, cause, gone. Even the concept of forever gets blurry. If nothing changes, can you even say time is passing? In this ultimate end state, the universe might exist, but not live. It might persist, but it can't tell a story, because stories need chapters, and the heat death erases all turning points. Physicists estimate this could take a Google years. That's a 1 followed by 100 zeros. A number so big it makes billions look like pocket change. In that time, black holes will evaporate through Hawking radiation, stars will fade to black dwarfs, and even protons may decay. Eventually, all that remains will be low-energy photons evenly spread across space, an undisturbed sea of nothingness. It's hard to say enough about how important this is. Entropy is linked to time, at least the way we think about it. When there is no more entropy, time stops moving forward. Today is today, and tomorrow is tomorrow. Clocks don't stop ticking, they just don't have anything to tick through. There is no longer any order, no way to move forward. Some theories suggest tiny quantum fluctuations might still happen, creating random blips in an otherwise dead cosmos. Others speculate on Boltzmann brains, spontaneous minds flickering into existence for a brief, pointless moment in the dark. But these are statistical ghosts, not narratives. They don't bring time back. They only prove how strange and empty the future will be. It's not just stars that die in the heat death. Things are coming to an end, the end of being different. And when everything is the same, when all the processes are over and all the gradients are flattened, time stops being important. In a way, though, this fate shows us how rare and beautiful now really is. The world is full of contrasts, like hot and cold, light and dark, work and rest. We live in a world where there are still ways to measure time. Gravitational waves and temporal warping. Space is like a sheet that has been stretched out. Imagine putting a bowling ball on it. The ball will sink and pull everything around it down. It's called gravity. When you put the ball down, what if you slammed it down so hard that it made the whole sheet ripple? Those swirls are gravitational waves, which are tiny movements in space-time. They don't just move space, they also change time. Einstein first forecast gravitational waves more than 100 years ago. This was a direct result of his general theory of relativity. His models say that when very large objects, like black holes or neutron stars, speed up or merge, they do more than just mess up the space around them. They change the universe itself with their waves. These are not waves of sound. They're not light. They are real waves in space-time that move at the speed of light and bend everything in their way, even time itself. When one of these waves passes through Earth, it stretches and compresses space ever so slightly. It also temporarily changes how time flows in that region. Imagine two identical clocks, one slightly closer to the source of a gravitational wave, the other slightly further. As the wave rolls through, those clocks will briefly tick at different rates. Not by much, fractions of a second, but it's real. Time itself wobbles as the wave passes. In 2015, the LIGO Observatory detected gravitational waves for the first time, confirming Einstein's prediction. What caused the signal? Two black holes smashing into each other over 1 billion light-years away. The energy released in that single event briefly outshone all the stars in the observable universe. And it wasn't just space that felt it. Time did too. The wave stretched time for everything it touched, just a little, but enough for humans to finally hear the universe's deepest tremors. What's truly wild is how gravitational waves bypass traditional signals. Unlike light, they aren't blocked by dust or gas. They carry undistorted information about violent events we'd otherwise never see. And because they warp time, they give us a new tool, a temporal probe. By studying how time is affected by these waves, we can learn about the geometry of space-time, the dynamics of black holes, and even the origins of the universe. Scientists now dream of using gravitational wave astronomy to look further back than ever before, past the cosmic microwave background, into the earliest moments after the Big Bang. The universe then was opaque to light, but it would have been transparent to gravitational waves. If we could detect those ancient ripples, we might finally glimpse the moment when time itself began to flow, or at least started to make sense. These waves don't just tell us about the past, though. They also teach us an important lesson about time. It changes all the time. It can be bent, stretched, and shook by mass and energy. There is no sound of time passing in the background. It is actively taking part in the movement of the world. Gravitational waves show this to be true. In the future, space telescopes like LISA, Laser Interferometer Space Antenna, will be able to pick up longer, more subtle waves from even bigger mergers, like giant black holes, neutron star collisions, and even hypothetical cosmic strings. And each wave they find will be like a mark from the very past. It will show not only where and when something happened, but also how time moved during that event. Time is not safe from the chaos in the universe as shown by gravitational waves. It doesn't tick away by itself, unaffected by anything else. It does flow, but it also shakes, trembles, and bends. There are times when time moves faster than light. So the next time you imagine space shaking from a faraway disaster, remember that time just slid through the quantum web of existence. Your heartbeat might stay steady, and your clocks might look normal. The cosmological constant, a ticking clock for the universe. In 1917, when Einstein tried to apply his new theory of general relativity to the entire universe, he ran into a problem. Gravity should be pulling everything inward, but the cosmos wasn't collapsing. It seemed static. To fix this, he added a fudge factor to his equations, the cosmological constant. At the time, it was just a mathematical patch, but today, it might be the key to understanding how time unfolds across the entire universe. Fast forward a century, and we now know the universe isn't static. It's expanding, and not just expanding, but accelerating. Galaxies are flying apart faster and faster, driven by a mysterious force we call dark energy. And the cosmological constant? It's back in the game. In fact, it might be dark energy itself, a constant energy density built into the vacuum of space, pushing everything outward. Here's the crazy part. If the cosmological constant really is what's causing this uncontrolled growth, it could be like a cosmic clock that keeps time moving at the fastest possible rate. In Einstein's equations, space and time are linked. So if the fabric of space is stretching faster, then the structure of time is changing with it. As the universe accelerates, it doesn't just grow, it also affects the rate at which time flows between distant points. The more dark energy dominates, the more space-time becomes warped, not by mass or motion, but by emptiness itself. And the cosmological constant, sitting there in the math like a quiet hum, keeps the tempo ticking. What's strange is how this changes what we expect. Matter and radiation ruled the early world. The expansion was quick, but it was slowing down. Inflation, nucleosynthesis, and the early formation of galaxies were just a few of the fast-moving events that made time feel tight. But when dark energy took over, which happened around 5 billion years ago, things started to speed up. Somehow, time began to get longer. Cosmic events happened less often. The galaxies moved farther apart. The universe's beat started to slow down, but not in seconds or minutes. Instead, it slowed down in cosmic rhythms, which are periods that last billions of years. And if the cosmological constant continues to rule the universe, then this trend will only get worse. In the distant future, galaxies will disappear over our horizon. Star formation will cease. Cosmic background radiation will fade into undetectability. In that far-off silence, time will continue to flow, but with nothing left to measure it. It'll still tick, but it will be meaningless. Some physicists propose that the cosmological constant defines a kind of universal timescale. Not like a ticking clock, but like a background beat that determines how fast the universe forgets its past. The bigger the constant, the faster space accelerates, the more time dilates across the cosmos. In that view, time isn't something flowing independently. It's being stretched and slowed by the cosmic vacuum itself. If the cosmological constant really is constant, that is, if it never changes, then the universe will get close to a de-Sitter phase, which is a state of empty, smooth, exponential growth. No weight, nothing in place. Space is being pulled apart by dark energy. And when that happens, time doesn't really matter. Time goes on even when there are no events, witnesses, or organization. But does it really matter? Others argue the constant might not be constant at all. In some models, it could decay, shift, or morph into a new field. If that happens, the expansion might stop or reverse. Time could slow down or even reverse its arrow. In some theories, the universe could crunch back down, bounce, and start again, rebooting time with a new clock entirely. One thing is certain: the cosmic constant is not just a number in an equation, whether it is or is not constant. It's a force that changes the speed and direction of time all over the universe. Time will move forward long after everything else has stopped talking. It's the beat behind the dance of worlds and the whisper that will carry it forward. In other words, when we talk about time on a global level, we're not just talking about seconds and minutes. We're talking about how things happen in the real world. The cosmic constant may also be the quietest and strongest timekeeper in the universe. There is no clock on the wall, not even a beat, but a push that will never end, stretching space and time into the future. Chronons, theoretical particles of time. What if things don't go as planned? How about if it's not a river that flows, but more like a flipbook, page by page? That's the crazy idea behind chronons, which are made-up objects that would be to time what atoms are to matter, the smallest unit that can't be broken down and is essential. They wouldn't just be something we move through if they were real. Time would be made of something. Chronons were first proposed in the 20th century by physicists like Ettore Majorana and later explored by thinkers like T.D. Lee and C.N. Yang. The idea goes like this: just as energy and matter come in tiny chunks, quanta, maybe time does too. In this view, there's a smallest meaningful slice of time, smaller than which nothing happens. No motion, no cause and effect, no before and after. Below that scale, time has no meaning. It's not smooth, it's pixelated. Think of a video. If the frame rate drops too low, you stop seeing motion, you see jump cuts. If the universe runs on chronons, then its frame rate would be determined by the size of those particles. Below that tick, you can't subdivide. No more microseconds or femtoseconds, you've hit the fundamental limit. How little does a chronon really be? Some ideas say it's the Planck time, which is about 5.39 x 10 circumflex 23 seconds. That's how long it takes light to move one Planck length, which is the shortest space that can be measured physically. If that's true, then the universe's clock speeds up by about 1043 times every second. Each click is a chronon. In between clicks, there is no action, there is no time. If time is quantized, then motion must be too. Nothing moves smoothly, it just appears to move smoothly because we're too big and slow to notice the jumps. Even something as fundamental as a photon crossing space would be happening step by step, click by click, frame by frame. Some of the biggest puzzles in quantum physics might be solved by this idea. The unpredictability of radioactive decay, the rapid jumps of electrons between energy levels, and even the probabilistic breakdown of wave functions could all be caused by the small scale of time. If the world has a tick rate built in, then things can only happen at the same time as those ticks. Chronons also challenge relativity, which assumes time is a smooth coordinate you can stretch and shrink depending on gravity and velocity. But if time is made of discrete chunks, then there's a minimum time that nothing, not even black holes, can compress. That would put an end to singularities. You couldn't divide space-time infinitely anymore. You'd have to account for the quantum structure of time itself. Chronon-based models of particle behavior have been tried by some researchers. These models try to show things like how electrons orbit nuclei, or how particles interact with fields. Instead of seeing time as a line, these models often see it as a series of separate steps. The end result? Some of the time, they fit what we see inside. Not always, though. The chronon is still an interesting idea, but it hasn't been proven to exist yet. If chronons do exist, then time wouldn't be a backdrop. It would be a substance. It would come in packets. You could count it. You could, in theory, even weigh it, if it had any mass at all. And just like photons carry light, and gravitons possibly carry gravity, chronons might carry the experience of time itself. This makes me think about the meaning of life and philosophy. Does this mean that the past and the future are made of the same stuff? Could you keep chronons? Could you go from one to the other? Just one chronon, or measure of time? What would it feel like if you could separate it from everything else? Most likely, nothing. Because everything needs to change. Awareness, thought, and perception. If you're stuck in a single slice, there is no before or after. It was just a frozen picture. So far, there's no direct evidence that chronons are real. We haven't found a quantum of time in our experiments. But neither have we ruled it out. And as we push physics deeper into the Planck scale, through particle colliders, quantum computing, and perhaps one day quantum gravity, we might get closer to an answer. The Great Silence. When the universe stops ticking. A very, very long time from now, no one will be alive to see a certain event. Not you, not aliens, not even black holes. A split second when everything stops. There are no stars, nothing hitting each other. There are no changes in temperature that could cause chaos. Not moving. Silence. Nothing has changed. Nothing but silence. It's not a creative metaphor. This is what science actually says will happen. The world will end in a period of time called the heat death. And it won't just be the end of everything when it does come. It will be the end of time. Because here's the unsettling truth. Time doesn't exist on its own. It's not floating out there in space like an invisible river, just flowing along no matter what. Time, in every sense that matters, is the measurement of change. It's what we use to describe movement, cause and effect, progress, decay. The second you remove change, time becomes meaningless. It's like trying to count the beats of a song that never starts. What then could really stop the world from changing? The world we live in is full of things right now. Light, heat, dark matter, dust, stars and gas clouds. It's going, alive in a general way. Stars are born, remain lit for billions of years, and then either blow up or fade away. A lot of planets move around them. Black holes eat things. Particles are moving, breaking down, and changing places right down to the smallest sizes. There's time because there's always something to compare, something to measure, and something to say. This happened after that. But every star has a deadline. Every black hole eventually evaporates. Every particle, in theory, may one day decay. Entropy, the tendency for systems to go from order to disorder, is always increasing. It's not evil, it's just the math of the universe. Over time, energy spreads out, gradients flatten, and usable heat disappears. Now picture a universe where entropy has finished its job, where everything has become one big, cold, dark soup with little activity, not a star. There are no black holes, no galaxies that glow, nothing to do. There are only particles floating in space, so far away from each other that they might as well be in different worlds. There is no action. There is no way for anything to happen. You can't do anything with that energy. And if nothing happens, what does a second mean? This is the Great Silence. Not just a pause, a full irreversible stop. It's like hitting the final frame of the longest movie ever made and realizing there's no sequel, no post-credits scene, and no audience left in the theater. In this era, clocks become useless. You could build a clock, in theory. Maybe something that vibrates or ticks or flashes, but what would it tick for? If there's no other system to interact with, no observer to watch it, no change happening outside its mechanism, then that ticking is just a ghost. No different from a rock silently existing in a vacuum. You can't measure time in a world where nothing else is moving. In that way, the death of the universe is really the death of time itself. Things are getting worse. Things don't end with a bang. The end is a whimper, a crawl that moves so slowly you might not even notice it ending. This isn't a supernatural event that takes place overnight. It takes a very long time. First, the stars go out. Then the galaxies get dark. Then black holes, which are the last objects with power, let radiation into the empty space until they disappear as well. What's left has so little life in it that the words before and after don't mean anything. At that point, the universe is a blank canvas. Not in the sense that anything new can be painted on it, but in the sense that nothing ever will be again. It is still, it is cold, it is empty, and it is eternal. Some physicists wonder, will time ever truly end, or will it just become so stretched and so irrelevant that it no longer has purpose? That's not an easy question to answer. Time is baked into how we understand existence. But if all clocks fail, not because they're broken, but because there's nothing left to tick against, does time really persist? Maybe that's what the Great Silence really means. Not just a universe without sound, but a universe where nothing speaks and nothing listens, where every action has already played out and the future is just a long empty hallway with no doors. The universe had a beginning, a burst of energy, chaos, fire and form. It created time by doing things, by moving. Now we know it may also have an end, not by destruction, but by the absence of motion. And when that final stillness arrives, it won't just be the lights turning off. Why clocks don't measure time, they measure change. To be honest, a clock makes you feel like you're looking at time itself. Numbers that glow, hands that tick, and little bars that jump every second. It's time, right? Not really. The catch is that clocks don't tell time, they tell change. The only reason you think it's time is because everything around you stays the same. A second isn't some magical slice of reality. It's a label we gave to a repeating motion. Historically, it was the time it took for a pendulum to swing, or for the sun to cross a shadow dial. Today, it's based on a specific number of vibrations inside a cesium atom, exactly 9,192,631,770 of them. And boom, that's 1 second. But look at the pattern. It's always motion, always change. Something that does something over and over, and we count the beats. A clock is just a machine that keeps track of regular changes. It doesn't do time itself. A crystal could be moving, a gear could be turning, or an atom could be switching between energy states. Something inside your wall clock is moving, not the hands. The numbers on your phone screen move around because the wires are switching on and off, not moving. Not enough time to read. What does that mean about time? It says that there is no such thing as time without change. Imagine that the whole world was frozen. Everything stops, every particle, every wave, every atom. Think about checking your watch. The second hand won't move. The gears are not moving. You're also frozen. Still able to say, a second has passed. How could you know? If there's no difference between one moment and the next, then there is no next. You're just frozen. Time, in that sense, is nothing but a way to describe differences between moments. And if no differences exist, there are no moments to compare. No before or after. No motion. No memory. Just stillness. You can't measure time in a world that refuses to move. This isn't just an intellectual thought. It is a part of current science. Einstein taught us that different people see time in different ways. It changes how it moves based on how fast you're moving, or how hard gravity is pulling on you. Time doesn't change in those settings. What changes is how fast things change between them. Your heart beats less quickly. Your clock moves more slowly. The particles in your body break down more slowly. Time is just a way to compare things. In other words, time is not a thing. It's a relationship between things. It's how we organize sequences of change. What if we stopped saying that took 5 minutes and instead said that took 300 heartbeats, or that took 1,000 footsteps, or 7 rotations of Earth's core? Sounds weird, but it's the same idea. You're still just counting how much something changed. We chose standardized clocks because they're convenient, not because they reveal any fundamental truth. This is why clocks don't work in isolation. If a clock ticks in a universe where nothing else exists, does it really keep time? Sure, it might count ticks, but what do those ticks mean? There's no frame of reference, no context, no events to compare. It's like a drumbeat in a void, rhythmic but irrelevant. Stranger still, Two clocks next to each other can tick at different rates if they are moving at different speeds or in different gravity fields. It's not a bug, it's just how things work. There is no such thing as a single universal time in the world we live in. Time changes, bends and twists. So, GPS systems would not work if satellites in space didn't keep changing their internal clocks. At first glance, it looks like their clocks are faster than ours. Once more, it's not time that's acting strangely. It's the world that's messing up the rate of change. What is this common thread that ties the world together, if not time? We just use it to talk about motion. That's it. Time is based on comparing how things change over time. Picture a show. You're seeing a long string of still pictures that have been played back quickly enough to make it look like they are moving. The movie is actually made up of 172,800 separate frames that play back at 24 frames per second. The movie's length is not its length in minutes, but the number of changes your eyes can pick up. Same with life. A human life isn't 80 years long. It's a heartbeat repeating 3 billion times. It's the Earth circling the Sun 80 times. It's cells dividing, hairs growing, skin wrinkling. It's changed. And time is just the label we attach to that journey of change. The speed of causality, time's hard limit. Cause comes before result in real life. The lift comes when you press a button. When you yell, an echo comes back to you. On the other hand, the world can't fall apart because of a hard rule. Causality can't move faster than light. It's not just a speed limit, it's also a time limit. It spells out when and what can change what. It's also one of the best signs that knowledge changes time itself. Let's start with the basics. According to Einstein's theory of relativity, nothing, not a particle, not a signal, not even gravity, can travel faster than the speed of light. That's about 299,792 kilometers per second. But this limit isn't just about motion, it's about order. If information could travel faster than light, effects could happen before their causes. You could see the punch before the fist is thrown. You could receive a message before it's sent. That would make the world end. This is why physics puts cause in a cage made of light cones. Think of an explosion. Its impacts spread out at the speed of light, making a cone-shaped edge in space and time. The blast can hurt everything inside that cone. What's outside? It's elsewhere, out of reach, unaffected, and not yet linked to time. This structure keeps the timeline tidy. It ensures that every event only influences events inside its future light cone, and is only influenced by things in its past cone. The speed of light isn't just a speed, it's a barrier between cause and effect. It defines what before and after mean. But there's something more important to this. Time and causality are linked. Time isn't just the passing of time, it's also the chance to have an effect. Something must be inside that cone if it can touch something else. Outside the cone, it might be real, but it's not in the present moment. That's why simultaneity isn't a fixed thing. Two events that seem to happen at the same time in one place might happen elsewhere in a different order. Causality is the judge. Now, this has strange consequences when you get into quantum physics. Particles, like entangled photons, can seem to affect each other instantly, no matter how far apart they are. Einstein called it spooky action at a distance. But even this quantum weirdness doesn't violate causality. You can't use entanglement to send a message faster than light. It's random. The universe protects its rule. Why is this such a big deal? Because it means that time isn't just something that passes. It's a structure built on what can and can't be influenced. Your entire experience of time, memory, action, prediction, is shaped by what causality allows. You remember what can have affected you. You plan based on what you can still affect. Time moves because information moves, and that flow can only go so fast. You could say that the speed of cause is the speed of light. This is also the reason why we can only see so far into the past or the future. What's available is set by our light cone, the radio background of space. Since the beginning of time, light has had this much time to reach us. Anything else is outside the range of our causality. It can't hurt us, and it can't even know we're there. It's there, but the present is different. And because dark energy makes the world grow faster and faster, more and more of it goes past that line of cause and effect. It's not that galaxies move away. They just stop being affected by us. Their time is not the same as ours. So when we talk about time moving forward, we're really talking about how causes work, the range of things you can touch, and the things that can touch you make up each moment. If you take away that framework, time has no shape. There is no order, nothing. Wormholes and time loops. Can we cut through time? Think about cutting a hole in a piece of paper and folding it in half. All of a sudden, two faraway points touch. That's the main idea behind a wormhole, which is a made-up path through space-time that quickly links two places. But wormholes do more than just cut off space. Maybe they'll also break time if the math works out. This would let you skip or even loop through history. Wormholes first came up in 1935, when Einstein and physicist Nathan Rosen theorized what they called Einstein-Rosen bridges. These were shortcuts in space-time that could connect black holes, white holes, or other cosmic anomalies, purely theoretical, unstable, untraversable, and doomed to collapse before anything could pass through. But in later models, physicists realized that if you could stabilize a wormhole, say with exotic matter that has negative energy, you might actually be able to travel through it. This is where time bends. Take one end of a vortex and speed it up almost to the speed of light, then bring it back. Because of special relativity, the end that is moving would have less time than the end that is not moving. It's like the twin dilemma, but with wormholes instead of twins. There's now a tunnel between two places in space, but they are in different times. If you walk through it, you'll feel like you've gone back in time. This kind of structure is called a closed time-like curve, CTC, a path through space-time that loops back on itself. In theory, an object following a CTC could return to its own past. You could meet your younger self, send information backward, break everything we know about cause and effect. And this possibility freaks physicists out, because once time travel is on the table, so are paradoxes. The grandfather paradox is the classic one. If you go back and prevent your grandfather from meeting your grandmother, then you're never born. So, how did you go back in the first place? To deal with this, some physicists propose the Novikov self-consistency principle. Any event that would lead to a paradox simply cannot happen. You might go back in time, but your actions will always end up supporting the timeline you came from. Free will? Maybe. But not the kind that lets you shatter the universe. Others suggest the universe would split into multiple timelines or branches. You change the past, but not your past. You create a new fork in the cosmic road. That's where wormholes and many worlds quantum mechanics start to dance together, blurring the line between science fiction and hard math. There isn't a real tunnel out there yet. We don't know if there is enough unusual matter to keep a star stable. It's still very hard to say what kinds of quantum effects, like entangled black holes, an idea called ER=EPR, might make wormholes happen. But the equations still let it happen. Even though Einstein's math is messed up because of general relativity, the door is still open. Wormholes might exist, and if they do, they wouldn't just be space savings, they'd be time cheats. What would it be like to go back in time through a wormhole? Would the world be frozen like an art show? Do you still want to age normally? Something might get back at you if you try to change it. Maybe time can be changed more than we think. These questions bring up a bigger truth that we don't yet know how to answer. A loop instead of a line. It wasn't a march, it was a maze. Neutrino oscillations and temporal ambiguity. They are so small, almost massless and almost transparent that people call them ghost particles. There are trillions of neutrinos going through your body every second. They come from the sun, supernovae, nuclear plants, and even the Big Bang. A very small amount of stuff affects them. They're not talking. Tricky. But these strange particles could be hiding a greater truth about time. The past and future aren't so different after all, and time doesn't move in a straight line like we think it does. Neutrinos change identity mid-flight. They come in 3 types: electron, muon, and tau, and as they travel, they oscillate between these forms. An electron neutrino might become a muon neutrino halfway through its journey, then shift again to a tau. It's like throwing a red ball across the room and having it morph into a blue cube before hitting the wall. But these shape-shifting antics aren't just weird, they violate expectations. In quantum mechanics, particles usually maintain a stable identity unless they interact. But neutrinos flip between identities without interacting, and they don't do it randomly. Their oscillation depends on how far they've traveled and how long they've been moving. That's where time creeps in and starts acting strange. To make sense of this, physicists describe neutrinos not as a single state, but as a superposition of mass states, quantum possibilities that overlap and evolve. As they move, the different mass states interfere with each other, causing the flavor, their identity, to oscillate. That's already mind-bending. But here's where time itself gets blurry. Because the evolution of these states isn't just spatial, it's temporal. Neutrinos don't have a precise, synchronized clock. Their quantum states evolve over time, but the definition of that time depends on the frame of reference. If you're standing still, you might see a neutrino oscillate a certain way. But if you're zooming through space at high speed, your version of that oscillation could look different. The ordering of events, which came first, what transformed when, becomes relative. Neutrinos may not follow time symmetry, especially T-symmetry, which says that physical processes should still look the same if time is turned around. In physics, most of the rules are T-symmetric. However, the T2K experiment in Japan and other experiments give us hints that neutrinos might not follow this rule. If this is true, it would mean that neutrinos act differently based on which way time is moving. To put it another way, they may be able to tell the difference between then and now. This makes a lot of questions come up. What does it mean for time to have an arrow if a particle can tell its direction? What makes neutrinos different from other particles when it comes to time? If so, what's the reason? What's so great about them? A few scientists even think neutrinos might be the answer to the question of why time moves forward at all. The idea is that symmetry violations, such as time reversal symmetry, are tied to imbalances in the world, such as the fact that matter is stronger than antimatter. Neutrinos might be holding the direction of time in place at the quantum level if they play a big role in these violations. Neutrinos have barely any mass. They're the lightest known particles with mass, and they travel just below the speed of light. That puts them in a strange in-between zone, close enough to light speed to behave bizarrely, but still tied to time in a way photons aren't. For photons, time doesn't pass at all. For neutrinos, it's complicated. Some ideas even say that certain neutrino actions might be signs of retrocausality, which means that events seem to be affected by what will happen in the future. It hasn't been proven, not very popular. Neutrinos, on the other hand, are the most likely objects to mess with time. When you're next sitting in the sun, know that you're being sprayed with messages from the heart of the sun that are very old. Some of them were born just now, some a very long time ago, and a lot of them are in more than one quantum state at the same time, flashing through time, making it hard to tell who they are and how things change. Quantum entanglement and non-local time. Two tiny things. They were made together and then sent to different parts of the galaxy. When you measure one, the other knows right away. There was no message sent, there is no weight, no limit on light speed, it just takes place. In physics, this is called quantum entanglement, and it's one of the most strange and uncomfortable facts. Most people are interested in how it breaks the rules of space, but what it really does is mess up our idea of time in a quiet, disturbing way. When two particles are entangled, they share a quantum state. Measure one, and the other's state is instantly defined, even if it's light years away. This happens faster than light can travel. Einstein hated this. He called it spooky action at a distance. And while he tried to prove it was an illusion, experiments have repeatedly confirmed the universe is indeed spooky. But here's what most people don't see. This isn't just a breach of physical space. It goes against the order of time. It doesn't matter when the measures take place to entanglement. There is still a link between the two particles, even if one is recorded after the other. It doesn't matter which came first, the math still works. In some sets of reference, A comes before B. In some, B comes before A. It doesn't matter to the connection. It looks like time doesn't matter. That's really scary. Because the way we see the world is based on the idea that causes come before effects. That you wake up and get out of bed. That one thing leads to another. But particles that are jumbled up break that chain. Aside from distance, they also don't care about time. Their relationship isn't inside it. This brings up the idea of non-local time. Non-locality in quantum physics generally means space, or how entangled states aren't limited to a certain place. But when you add relativity to the mix, you see that the problem is more complex. Entanglement is not limited by time either. The link between cause and effect gets fuzzy. No longer is the idea of when something happens set in stone. In some interpretations, like the transactional interpretation, entangled particles are described as exchanging information backward and forward in time. One sends a signal into the future, the other sends one into the past, and they agree on an outcome. It sounds insane, but it works with the math. It even preserves causality in a weird inside-out way. There's also the two-state vector formalism, which treats quantum systems as evolving both forward and backward in time simultaneously. A measurement today might depend not only on the system's past, but on future boundary conditions too. Meaning, the future influences the present just as much as the past does. Because if time can flow backward and forward, and particles can maintain coherence across that blur, then the arrow of time, what we call past and future, isn't built into the fabric of the universe. It's a construct, a convenience. The quantum world doesn't play by our rules. What we call now might be just a thin slice in a broader, timeless quantum landscape. In that landscape, entangled particles aren't communicating faster than light. They're not communicating at all. They're just two ends of the same quantum object, existing in a place where time doesn't apply the way we think it should. What does this mean for us? This suggests that the idea of cause and effect may have come about on its own. Something that you can only see when you look past the quantum level and into our messy, hot, and disjointed macro world. In the depths of truth, cause and effect don't work. Time can't stop entanglement because it goes deeper than time. The delayed choice. Experiment time-bending observations. You send one photon through a thing. It should behave like a particle and either follow one direction or the other, right? When you do the delayed choice experiment, however, the photon doesn't seem to care when you look at it anymore. It acts like the choice you are making now is going back and changing what happened in the past. One of the most disturbing things about quantum physics is that the choices you make now could change what reality looked like just now. The original double-slit experiment already showed us that particles like photons or electrons behave like both particles and waves, until you measure them. If you don't observe which slit they go through, they interfere with themselves like waves. But if you do measure the path, they act like particles, and the interference pattern vanishes. Observation changes the outcome. In the 1970s, however, scientist John Archibald Wheeler asked a more serious question. What if you wait to decide to watch until after the particle has passed through the slits? In other words, you let the particle choose a path or a wave-like behavior, and then you decide all of a sudden whether to watch it or not. What happens? Astonishingly, the results change based on your delayed decision. If you observe, the interference pattern disappears. If you don't, it reappears, as if the particle knew all along what you were going to do. But how? The decision came after the particle had already moved through the slits. It's like you reached backward in time and told the photon, actually, don't act like a wave, be a particle instead. And it listened. A lot of different kinds of light, atoms, and even electrons have been used in different versions of this experiment. And each time it proves the same strange truth. Reality doesn't become fixed until it's measured. If you want to change how the photon behaves in the past, you have to choose when to do it. This experiment is even stranger when done with a quantum eraser. In this case, you let photons pass through slits and use entanglement to mark their path. After the photons hit the device, you can either delete or keep that path information. There is no confusion if you keep the information. There is only particle activity. The interference pattern comes back, even if you delete it after the event. Think about that. You're erasing a piece of information after the event has already happened, and yet the outcome changes. It's as if the universe is saying, "Don't worry, I'll go back and fix that for you." What does this mean about time? In the quantum world, this means that the line between before and after starts to blur. The date isn't set in stone. It's not even a schedule. It's a list of possible outcomes, a web of outcomes ready to break apart when something is observed. And the decisions you make in what you think is the present seem to have effects on both the present and the future. Does this violate causality? Not in a way that lets you send messages to the past. You can't change history in a meaningful, communicable way, but it does suggest that the future can influence the present, and the present can retroactively shape what we thought the past was. This leads to crazy ways of thinking about quantum physics. The transactional interpretation says that particles trade offer and confirmation waves, which are messages that go both forward and backward in time and meet in the middle to make an event. From this point of view, every encounter at the quantum level is like shaking hands across time. And in the many worlds interpretation, every possible outcome happens in its own branching universe. Your delayed decision doesn't change the past. It simply determines which universe you observe, retroactively editing the storyline you're aware of. Where does that leave time? It just hangs there. Not sure. It's not longer a clean straight line from the past to the future. Instead, it's a jumbled web of possible futures and unfinished pasts that only seems to fall into place when we look, and maybe just for us even then. It's not just that the delayed choice experiment blurs the line between spectator and watched. It makes the line between now and then less clear. Hawking radiation and temporal reversal. Dark matter and black holes are the most dense places in space. Not even light can get out of them. But Stephen Hawking suggested something totally new in the 1970s that turned that idea on its head. Black holes aren't truly black. They shine, they let water in, they go away. This strange process, called Hawking radiation, may even mess up time itself. It doesn't just break the rules of black hole physics. At its most basic level, the theory suggests something crazy, that time can go backwards in a black hole. So what is Hawking radiation? At the edge of a black hole, the event horizon, quantum fluctuations constantly create pairs of particles and antiparticles. Normally, they annihilate each other instantly, but near the horizon, one particle can fall in while the other escapes. The escaping particle becomes real, and the energy needed to create it is subtracted from the black hole, causing the black hole to lose mass. That is, black holes slowly disappear one quantum leak at a time. For big black holes, this process takes billions of years, which is way too long, but for very small black holes, it speeds up. They give off radiation faster as they get smaller. Just as they're about to go away, they explode with energy and disappear. People have always thought that once something goes into a black hole, it's gone forever. What would happen to the data that fell into black holes if they disappeared? Where does it go? There is a strict rule in physics that says you can't delete data. That's not good if Hawking radiation doesn't carry any signs of what made the black hole. It's called the black hole information paradox, and we might have to change how we think about time to solve it. Some solutions propose that the information gets imprinted in the Hawking radiation, but in a way that only becomes clear near the end of the black hole's life. In that model, the outgoing particles carry pieces of the past, but only when time is nearly up. It's like a message that only reveals itself after the whole story ends. The timeline doesn't reveal itself linearly, it plays backward, unraveling the black hole's history in reverse. Some models suggest that, inside the black hole, the flow of time could reverse entirely. When you cross the event horizon, space-time warps so dramatically that the roles of time and space flip. Moving inward becomes like moving forward in time, and at the singularity, if it even exists, the arrow of time could snap backward, causing a bounce, a new expansion, or even the birth of a new universe. This idea comes up in theories of the unknown, like black hole cosmology, which says that every black hole could create a new world inside it. Time could go in the opposite way in those worlds. From our point of view, it's the end. It could be a start from the inside. The idea that Hawking radiation doesn't just show what happened in the past is even more radical. It might be able to reverse the interaction between particles, putting together earlier states backwards. This view says that the black hole is like a pause button, sending out jumbled pieces of its own formation, not in order, but as an analysis of its own past that goes backwards. Is this proven? Not at all, not yet. But the math behind Hawking radiation and the search for a theory of quantum gravity keep showing us that our ideas about time are not as solid as we thought they were. Things might not work the way we think they do inside a black hole. Things could go in the opposite direction. Information that comes in could be jumbled or delayed on its way out, but it would not be lost. What does that say about time? That it might not be fixable, that the past and the future are more connected than we thought, that the most mysterious things in the world aren't just eating stuff, they're also changing the way of time. Closed time-like curves time travel in Einstein's math. It sounds like science fiction to go back in time. Einstein's general theory of relativity, on the other hand, has a logical flaw that makes it seem like it might be possible. These aren't DeLoreans or phone booths that spin. They're called closed time-like curves, CTCs, and they're thought to be lines through space-time that loop back on themselves, letting you go back in time. Einstein's equations show that space and time are not two different things, but rather two parts of the same four-dimensional cloth called space-time. This cloth can also bend, twist, and loop in some very bad situations. The name of the thing is exactly what it sounds like, a path that starts in space-time and ends up back at the same place in time and space. If you could find a way to do it, you might be able to shake hands with yourself from 5 minutes ago, or tell yourself not to send that dangerous text. So where do these curves come from? Some solutions to Einstein's equations naturally allow for CTCs. One of the most famous is the Gödel metric, discovered in 1949 by mathematician Kurt Gödel. Yes, the incompleteness theorem guy. He showed that in a rotating universe, a very specific kind, you could loop back through time using the warping of spacetime itself. The math worked, the physics, not so much. Gödel's universe requires conditions that don't match what we observe, but it proved something huge. General relativity allows time loops. Other theoretical objects, like rotating black holes, Kerr black holes, and cosmic strings, infinitely long superdense filaments left over from the early universe, might also create space-time geometries where CTCs could form. These configurations could twist space-time so intensely that a traveler could leave a point and return to it before they left. But there's a catch. Paradoxes. Clues are broken by CTCs. The grandfather paradox is the most famous thought experiment. In it, you go back in time and stop your grandfather from meeting your grandma. If you do well, you'll never be born. How did you get back in time to stop him if you were never born? Physicists have proposed several ways around this. The Novikov self-consistency principle, for example, says that time travel is only possible if your actions in the past are already part of history. In other words, you can go back, but you can't change anything in a way that creates a paradox. If you try to stop your grandfather, something will always get in the way. You'll drop the gun. The train will be late. The universe will self-correct. Another approach is the many worlds interpretation. Maybe traveling into the past creates a new timeline. A forked universe where your changes apply, but your original reality remains untouched. You don't kill your own grandfather. You kill an alternate version's grandfather in a parallel timeline. Cold comfort, but at least no paradox. Even if CTCs are mathematically allowed, they're probably physically impossible. Most models that allow time loops require exotic matter, stuff with negative energy density, to stabilize the loop and keep it open. That kind of matter has never been observed in the quantities needed. And according to Hawking's chronology protection conjecture, the universe has a built-in mechanism to prevent time travel. Quantum effects become so wild near a time loop that they destroy it before it forms. Reality, in other words, protects its timeline. But we can't forget about math. There are still CTCs in real answers to Einstein's equations. They are still possible. They only need conditions that are extreme, strange, and probably something that no society, no matter how powerful, will ever be able to do. Still, they're there, being sneaky in math. Something to remember that time as we know it can be stopped. It could fold if there is enough force on it. With the right shape, it could loop. Time inside a neutron star. Does it even exist? When a very large star goes supernova and falls apart, what's left is a neutron star. A thick ball of matter is all that's left. A teaspoon of it would weigh more than 1 billion tons. Space and time bend like taffy because of how strong the gravity is. Time stops for a while. Let's start with how neutron stars warp space-time. According to general relativity, mass curves space and slows down time. The more massive and compact something is, the stronger the effect. Near a neutron star, gravity is thousands of times stronger than that of Earth. So if you stood on the surface of a neutron star, you wouldn't survive but go with it. Time for you would crawl. Seconds for you could be hours or days for someone farther away. This is called gravitational time dilation, and it's not just theory. We've seen it in action. Even GPS satellites around Earth have to account for it, or they'd be off by kilometers every day. Now imagine how wild that effect becomes near a neutron star. If we could get inside the neutron star, time might not make any sense. Inside, there is a lot of quantum doubt and a lot of pressure. Atoms can't live here. There are neutrons made from even protons and electrons being smashed together. This matters before it turns into a black hole, when it is at its smallest. Time slows down and stretches out more as you go deeper into the Earth. Researchers in the field of physics think that close to the center, time might slow down or act in ways that we can't fully explain with known physics. It's not entirely clear if a traditional concept of time even exists inside a neutron star's core. When space-time is warped to such an extreme degree, the usual relationships between distance, duration, and causality start to fall apart. The rules get fuzzy, the coordinates get messy. Time may not be linear. It may not even be sequential. What does that mean? Imagine being in a place where things don't happen in a straight line, where the past and future are warped into weird loops that merge. It's even possible that space-time could change into a different form deep inside dense things like neutron stars, similar to how water changes into ice or steam. During this phase, time may start to show up as a result of deeper factors we don't fully understand yet. Even the math gets shaky here. General relativity works great at large scales, and quantum mechanics rules the tiny. But neutron stars sit at the border, too massive for quantum rules, too small for general relativity. We don't yet have a theory of quantum gravity to truly describe what happens at the center. Could time go around and around? Could it stop? Could it break up into pieces we can't see? We're not sure. One thing we do know is that if you stood on the surface of a neutron star and looked out at the universe, time would seem to fly by very quickly. The galaxies would spin faster. Stars would go from bright to dim in an instant. People outside of your world would think you're moving slowly or even frozen in place. And the reverse is true too. To someone watching you from afar, your clock would be ticking slowly. If you left after 1 hour on the star, Earth might have aged decades or centuries. It's not just science fiction, it's a very real measurable consequence of extreme gravity. So does time exist inside a neutron star? That depends on what we mean by exist. If you define time as a sequence of events, a ticking rhythm that orders cause and effect, then maybe not, at least not in the way we understand. Inside that crushing gravity and nuclear soup, time could be distorted beyond recognition. It might run, stall, twist, or vanish entirely. Multiverse models without shared time. It seems like time is the only thing we all share. There is no difference between being on a beach in Bali and being on the far side of Pluto in space. You are still living in the now and moving forward one moment at a time. But time might not be something we all share if the multiverse is real and there are other worlds besides our own. In many models of the universe, time doesn't even work the same way in different worlds. Or even worse, it doesn't exist. Let's start with what the multiverse even means. There isn't just one version of this idea, there are many. Some come from cosmology, others from quantum mechanics, and a few from string theory. But a common thread in several of these models is this. Each universe might have its own laws of physics. And if the laws of physics are different, that includes how time behaves, or whether it behaves at all. Take the eternal inflation model. After the Big Bang, space didn't just expand, it inflated rapidly, driven by a kind of vacuum energy. But inflation didn't stop everywhere at once. In fact, it may still be happening in pockets of the cosmos, creating bubble universes, where inflation ends and Big Bangs begin. Each bubble becomes its own universe, with its own constants, particles, and potentially its own definition of time. In this model, time doesn't flow the same across bubbles. Two universes may have different arrows of time. One might be expanding forward, while another could be collapsing. Or even more bizarre, some universes may have no time at all, just static configurations of space, like a frozen photograph of existence. Quantum physics also led to other ideas, such as the many worlds explanation. In this case, every quantum choice breaks reality into different paths. If this is true, then there are many forms of you, one for each possible result. But do these branches share a clock that is in sync? Not all the time. They're not follow-ups. They happen at the same time, but they don't talk to each other or affect each other. In some branches, what seems like the future could be the past, or they could be totally cut off from each other in time. Then there's string theory, which suggests the universe is made of tiny vibrating strings, and that there may be 10 or 11 dimensions, some of which are compact and hidden. In some versions of this theory, time doesn't appear in the base equations at all. It's not fundamental, it's emergent. Just like temperature comes from lots of molecules moving around, time might emerge from patterns in a deeper reality. And in other universes built from different string vibrations, time might never emerge at all. Physicist Sean Carroll has suggested that time, like temperature, might be a feature of large complex systems. The more disorder, entropy, the more obvious the arrow of time becomes. But in some baby universes, freshly formed low-entropy realms, there might be no clear direction for time. Everything just is. No past, no future, just configuration. This makes the idea of a shared timeline across the multiverse meaningless. There's no universal clock ticking through all of creation. Instead, each universe may have its own time, or a warped version of it, or none at all. Because we're so used to thinking of time as this backdrop that everything moves through. But that backdrop may only exist here, in our corner of reality. Step outside this universe, and you might step outside of time entirely. You wouldn't arrive before or after. You'd arrive in nowhere. What exactly does this mean? There's a chance that we wouldn't get to a different time if we could use a wormhole or quantum doorway to go to another world. We might get to a place where time doesn't exist, where causality doesn't work, and where our minds can't even understand what's going on because we developed in time and can't work without it. Or maybe the act of observing would generate time locally. Maybe time is something that only exists when something is watching. That sounds like science fiction. But in the weird rules of quantum physics and multiverse cosmology, it's a question scientists are actively trying to answer. Cosmic microwave background, the universe's first clock. If you could turn off every planet, star, galaxy, and light source, you could sit in space and feel it even if it was dark. A hint of heat. There was a dim afterglow that hummed through the space. The cosmic microwave background, or CMB, is what she saw. And even though it looks like nothing, that light is the oldest in the universe. It's the closest thing we have to a cosmic clock that can tell us when time as we know it started. Let's rewind 13.8 billion years. The Big Bang wasn't an explosion in space. It was an explosion of space. In its first fractions of a second, the universe was smaller than an atom, hotter than any furnace, and expanding faster than anything we've ever seen. But for the first 380,000 years, the universe was basically invisible, too hot, too dense. Atoms couldn't form, and light couldn't move freely. It was like being inside a glowing fog. The time of recombination. It got just cool enough in the universe for protons and electrons to join together to form hydrogen. All of a sudden, light could move around easily. The CMB is what we now call that first light. It shows the universe as it was 380,000 years ago, when it was still very young. But the CMB is more than just a photo. It's a timestamp, a cosmic receipt. By studying the exact properties of this light, its temperature, its spread, its tiny fluctuations, scientists can measure the age, shape, and evolution of the entire universe. Every hot spot, every cold spot on that ancient sky map tells us something about time itself, how it stretched, how it curved, and how it began to tick. The CMB isn't just background noise. It's everywhere. No matter where you look in the sky, it's there. And it's incredibly uniform. The same in every direction, down to 1 part in 100,000. That consistency tells us that the early universe must have been in tight communication with itself. But how could it do that, when light hadn't had time to travel between regions? This is known as the horizon problem, and it led to one of the most mind-bending ideas in cosmology: cosmic inflation. In this theory, a tiny fraction of a second after the Big Bang, the universe ballooned out faster than the speed of light. This rapid expansion smoothed out the wrinkles and let every part of the universe agree on the rules, including how to measure time. The CMB isn't just old light then. It's a line that connects the eternal chaos of the beginning of the world to the steady flow of seconds and minutes we live in now. There was no light to measure before the CMB. There is no clock to strike. We can't see anything before or after. The CMB is where time in space really starts to matter, and we still have its mark on us. Some of the CMB can be picked up by your TV, your phone, and your Wi-Fi. That snow you see on a TV that isn't tuned in, that comes from the CMB about 1% of the time. You are seeing time itself come into being. The CMB does, however, set a ceiling. We can't see beyond it. Not because there's nothing there, but because light hasn't had enough time to reach us from before that point. It's a cosmic wall, the edge of our observable universe. Whatever came before, if before even makes sense, lies behind that veil. We can only infer, we can't witness. This means that the cosmic microwave background is not only the first light, but also the first clock-in the world, because that's when time put on its hard hat and began making everything we see. Since then, that first tick has been used to count every second, star, breath, and heartbeat. And maybe the world will end again when the last star dies and the last atom breaks down. But for now, when we look at the CMB, we see more than just radiation. The dark flow, a motion beyond observable time. Something is out there. There is a force pulling whole groups of galaxies toward a faraway spot in the sky. It's something we don't know. It's going somewhere we don't know. We only know that it doesn't care about the rules of the universe that we can see. Not only is this a puzzle of space, it's also a direct challenge to how we think about time. The phenomenon is called dark flow, Discovered in 2008, it began with astronomers analyzing the motion of hundreds of galaxy clusters using data from NASA's Wilkinson Microwave Anisotropy Probe, WMAP. They were measuring the kinetic Sunyaev-Zeldovich effect, basically how galaxy clusters interact with the cosmic microwave background, CMB. What they found wasn't random. Instead of drifting in all directions like cosmic tumbleweeds, these massive clusters, millions of light years across, were all moving in the same direction, quickly, very quickly, at about 2 million miles per hour. All of them are moving toward an area of sky near Centaurus and Vela. This didn't go as planned. This kind of group drift shouldn't happen in a world that had a smooth Big Bang and is ruled by dark energy that is spread out evenly. It's like finding all the boats in the water going very fast toward one island, even though there shouldn't be any islands there. So what could cause dark flow? One hypothesis is terrifying in its implications, that these galaxies are being pulled by something beyond the observable universe. Something massive, something ancient, maybe even a remnant from before the Big Bang, or a neighboring universe with its own physics and its own time. The observable universe isn't the whole universe. It's just the part we can see. Light from anything beyond a certain distance hasn't had time to reach us. But if galaxy clusters are responding to gravity from beyond that limit, then they're interacting with something that lies outside our space-time horizon. And that means our concept of now doesn't apply. So you can see that time and space are linked. You can see further back in time as you look farther away. The dark flow does affect the groups though. They could be drawn to something that doesn't happen at the same time as us. A part of the universe that has a different clock, or none at all. This brings up a scary question. Is time the same everywhere? Dark flow gives us a hint that the answer might not be yes. If there are forces in the world that are outside our light cone and that we can't see or deal with, then time could move faster, slower, or not at all in those areas. It's like having two clocks that never agree on when to tick, or even worse, two clocks that disagree on what a tick is. Some scientists think this shows a multiverse interaction or a space-time leak in which gravity moves between worlds. If it's true, dark flow could come from an old structure in a different world that pulls galaxies toward a place where time and physics don't work. Others go even further and say that the world we see is just one bubble in a huge ocean of space, and dark flow is the wave from a bubble next to ours that brushes against ours. So our schedule is not set in stone, it's close by, like a time zone in the world as a whole. The trouble is that we can't see the cause. Dark flow has a reason that is outside of the cosmic microwave background, which is like a wall. We can't get any light, sound, or proof from the other side of that wall. We're now looking at motion, which is a result without a cause and a change without a setting. Can we even say when it began if we can't find the cause? For time to work, there must be a cause and a result. The sequence falls apart when there isn't a clear cause. Despite multiple studies since 2008, dark flow remains controversial. Some astronomers argue the data was flawed or misinterpreted. But even if dark flow doesn't exist as originally proposed, the possibility it opened still haunts cosmology. We learned a very important lesson. Motion doesn't always stop at the edge of time. There are no lines in the world like there are on a video game screen. Things can come in from places we can't understand, from places that don't follow our rules or our clocks. Don't just look down black holes or inside quantum loops if you want to find the moment when time stops. The expansion of space-time's constant disruption. Imagine pulling a bubble tight while tiny ants walk across the top of it. For the ants, it looks like everything is moving apart. That's what's going on with our world. Not just the area around us, but all of space itself is getting bigger. Time is also being twisted, stretched, and bent in ways that go against our most basic feelings. Since space is growing, the speed at which time moves is also not stable. Since the Big Bang, the universe has been expanding. But it's not like galaxies are flying away through space. It's more accurate to say space itself is growing, and galaxies are being carried along for the ride. The farther something is from us, the faster it seems to be receding, not because it's moving through space, but because the space between us is increasing. Now here's the twist. As space expands, it changes how we experience time. It literally disrupts the beat of the cosmic drum. Time isn't a metronome ticking in the background. It's tied to the fabric of the universe. When that fabric stretches, so does the rhythm. Redshift in space is one of the most striking ways that this is shown. When we look at galaxies that are far away, their light is stretched out into longer, redder waves. That's not just the Doppler effect, it's also a warping of time. Light from a galaxy billions of years ago was stretched by the expanding universe. This meant that it aged, flickered, and faded more slowly out there, not because the galaxy was moving, but because time was moving at a different speed. It gets even stranger as you speed up. Scientists found out in the late 1990s that the growth of the universe isn't slowing down, it's speeding up. In other words, space is not only getting bigger, it's getting bigger faster all the time. Who did it? Evil power. Even though we don't know what it is, we do know that it pushes galaxies farther apart. That also changes time. If dark energy keeps accelerating space, parts of the universe will drift so far away from each other that they'll effectively fall out of communication. Light won't be able to cross the growing gap. That means, in the far future, entire galaxies will blink out of existence, not because they're gone, but because time between us has been stretched so much their light can never catch up. To put it another way, growth isn't just a problem with space, it takes too much time. This is where it hits home. Even how you see now is different for everyone. People watching the same supernova might not agree on when it happened, if they are in different parts of the world. They may not even agree that it took place yet. Time doesn't move the same way everywhere. Because space is expanding, now is a neighborhood event, like the weather. It's not always the same, it's not absolute. Others go even further and say that cosmic expansion isn't just stretching space, it's also breaking down the idea of time as something real. As the world expands, its parts become less linked to each other. And with no communication, no change, no hint, how much time is left? Some people think we've been lied to from the start. We think time moves because we're in a space bubble that's getting bigger, and if we could go outside, if that's even possible, we'd see all of time at once. That's all. No past, present, or future. Just form. A huge, stretched-out shape that is stuck in space-time. But until then, we are prisoners of motion. We measure time by orbits, rotations, ticking clocks, decaying atoms. And as the universe expands, even those anchors start to wobble. Time becomes slippery, less absolute, more fragile. The world is expanding because of an unknown force that is pushing space apart faster and faster. This force is quiet, can't be seen, and never stops. It's known as the cosmic constant by scientists. Some people think it's more than just a force that controls growth. They think it might be the universe's only clock. When Einstein first laid out his equations for general relativity, he didn't like the idea of a dynamic expanding universe. So he added a term to his equations, a fudge factor, to keep the cosmos static. That term was the cosmological constant, often represented by the Greek letter lambda. Later, when astronomers discovered the universe was actually expanding, Einstein called it his greatest blunder. But it wasn't even a mistake. Let's go back to the 1990s. Two groups that were looking at supernovae far away found something shocking. The universe wasn't expanding slower, it was expanding faster. Over time, something was pushing galaxies farther apart than gravity could hold them together. That something looked a lot like the cosmic constant that Einstein talked about. It wasn't just holding things still this time, it broke everything apart. We now attribute this effect to dark energy, a mysterious substance that makes up about 68% of the universe, and the cosmological constant might be its mathematical fingerprint. a constant value woven into the equations of spacetime, dictating how fast space stretches over time. Because if lambda really is constant, unchanging, steady, reliable, it's like a metronome baked into the universe, a force that ticks out expansion at a consistent pace, stretching the fabric of reality moment by moment. Not a clock you can see, but a rhythm that everything in the cosmos is dancing to. In this way, the cosmological constant might be keeping track of time for the whole universe and setting the beat for its fate. When kappa speeds up expansion, galaxies move farther apart and the universe gets cold, empty, and lonely faster. Everything would be different if degree was just a little bit different, a fraction of a percent higher or lower. If the constant was bigger, the universe would have grown too quickly for stars to form, something less strong, and gravity might have pushed everything back into a big crunch. It's that precise, that is crucial, and yet, we don't know what it is. Is it the energy of empty space, a property of quantum fields, a placeholder for something even deeper, like vacuum energy or a fifth force of nature? Or is it a sign that time is emergent, that what we think of as passing moments is really just growth emerging with the help of this constant? Cosmological constant might last longer than everything else if it is really constant. It will still be there after all the stars have died, all the matter has broken down, and the last black hole has disappeared, stretching space-time in silence, moving forward without sound. What does it say about you if time isn't moving, but is instead bending, breaking, or maybe it never existed? About your past, your present, and your place in the universe? One thing is for sure, the real world is stranger than any clock. If you want to keep questioning what you thought you knew, then sign up for Beyond Horizons and go further into the unknown. The world isn't just getting bigger, it's also falling apart.